Good morning, all. Ah, thank you, thank you. As soon as I get organized here, I will. I don't want this. Oops, not here. Okay, that is gone. You can see my screen. Oops, not this. Sorry. All right. Please let me know. You can see the screen, right? Okay. Thank you. Thank you. Well, let's get this rolling. I hope the our introduction to the fluidized beds and fluidized bed technology was simple enough for everybody to get the basic understanding and idea. Now we are going to go for the applications, and of course, one of the most common application is combustion. That is the primary reason why this technology, fluidized bed technology, is advanced to its level that we see today. So, basically, we talked about two different types of fluidized beds. They both, I did not mention it to you yesterday, but needless to say, they both operate at ionization, travels through the bed in the form of bubbles, and they enlarge as they ascend, and sometimes they coalesce, they get bigger, or they are the ones that promote some sort of mixing in the bed, dense bed, and above the dense bed in the freeboard region, they erupt and traject particles into the freeboard. In the case of circulating fluidized bed that operates under the fast fluidization regime, no longer bubbles there because it passed the turbulent stage, and you have dispersion of particles and clusters. Okay, in both cases, we can assume that these are reacting flows. That means there's a mixture of fuel and air reacting in these cases. Okay, so let's start with the bubbling fluidized beds. Again, the particles there, let's say the bed, inert bed material is sand, and the fuel, a solid fuel, is fed into the bed. Um, this is from historical perspective. They are most, of course, plausible to use when fuel is solid. Okay, to burn a solid fuel, let's say a stoker, where you have a mass of fuel sitting there, you don't get the full benefit of contact. In other words, you don't maximize the air or oxygen to surface area combination. In a fluidized bed, this is a lot better, and then you can then burn a variety of solid fuels from um, coals of low calorific value to biomass or waste or even sewage sludge in these cases. Um, so this is the basic idea. You burn it either in a bubbling bed, which is here, and this is what we are covering. I want you to pay attention to the temperature, operating temperature range. It's between 760, well, this is not, could be as high as 900, but we don't want to go there. So usually in my designs, I always keep it at 850, which is a safe value for a variety of reasons that I will expand on more. Particle size, again, it could be different particle sizes. Um, And you have to understand that in this environment, uh, you don't really need to have perfectly round particles. By the attrition effect of the bed, particles, if they have sharp edges, whatever, they break off. They're filed off, and they become almost spherical. You can use lower fluidization velocities. Why is it important to use lower fluidization velocities? Then you don't have to have very large blowers because these are high capacity, high pressure blowers. They're very expensive as a capital cost, but also a very expensive to operate. It requires a lot of electricity. But nevertheless, you can reach high heat transfer rates and efficiency, and they are less sensitive to the fuel moisture. Um, you will say why? Because I pointed this out later on. You have a large thermal mass here. Once the bed is running, combustion is taking place, and it reaches a steady state. Uh, Whether the fuel moisture is 20% or 25% won't make a big difference because you usually have 5% fuel, 95% bed material. So in this large thermal mass, it won't affect the overall temperature. Okay, and overall temperature is important, of course, to keep it efficient. In circulating fluidized beds, we can try a little higher temperatures. Of course, fuel particles, they could be around even larger, given the, of course, a transition velocity and to fast fluidization. You will have to use higher fluidization velocities. Uh, but this, of course, given the nature of this configuration, you can burn much larger amounts, much larger amounts of fuel in a continuous fashion. It's a lot easier for ash removal and other things, especially, and I'm going to touch on solvent utilization. So here, a quick summary of parameters around bubbling fluidized beds and circulating fluidized beds when it comes to combustion applications. Okay, as you could see, one of the last point I mentioned, there's no solid circulation for bubbling beds, even though it can be forced, but in CFBs, it's more natural, and you can adjust how much you want to do. Okay, so this table will give you, if you were to design one, either bubbling fluidized bed or circulating fluidized bed, it will give you the operational ranges that you can start from. No design will be finite in the beginning. You start with these conditions, you pick the ranges, you go design it, iterate, come back and fine tune it until you have confident design. So before we go further, I think it's important to remind our basics in thermodynamics as to where we place, what's the place of either bubbling bed or circulating fluidized bed in this total thing. You'll remember your simple Rankine cycle, that objective is to produce high pressure, high temperature steam that could be fed into a steam turbine, will expand there, and then turn a generator, and the generator will, of course, produce electricity. Then the low quality, low pressure steam is condensed in the condenser, and then its repeater pumps. Okay, I should also remind you that the most inefficient part of any of these cycles is, of course, the condenser. That because of this, the maximum efficiency is limited let's say in good case to 42%. That means if you burn 1 kilogram of fuel cycle, you only get to utilize 40% of it in the form of electricity. The chemical energy of the fuel is only converted into electricity as 42% or 40%. So just I want you to remember this, and our objective is to use a different type of boiler that could maximize at least the combustion efficiency. So since most of the fluidized bed combustion applications, in most applications, coal is the fuel, I think we'll spend a few minutes on what is coal. It's an evolution, of course, over thousands and thousands of years. It comes from plants to peat to lignite. Under pressure and heat and time, it becomes coal, and that we know it as a different, like in four categories. Anthracite is the kind of coal that has the highest carbon percentage. Bituminous or subbituminous are the coals that are mostly used in power plants. And lignite is the worst type of coal, as you could see from the chart, that has a lot of moisture and a lot of ash. But nevertheless, in very many countries, because this is it's available and it is used, it is not the ideal fuel, but nevertheless, it's used widely, causing a lot of environmental issues, of course. Okay, so one final thing, if you divide a coal in 4 parts, fixed carbon is the part that will give you the char combustion. Volatile matter is the gaseous matter that under heating conditions or under pyrolysis, it will be released. Then the remainder, of course, moisture will be moved immediately whatever it is, and then the remainder will be ash, okay, which has a variety of materials. Okay, so again, before we talk about a fluidized bed combustor, let me just take you to the most common furnace or boiler in the world, that is a pulverized coal-fired power plant. Okay, in this case, you think of your car. In the car, you have a fuel injector. The idea of the fuel injector is to atomize a liquid fuel into a mist to give you the largest amount of surface mass to surface ratio, or volume to mass to volume ratio, which is represented by surface area that is exposed to oxygen, to give you the highest combustion rate. In this case, pulverizers, they mimic atomizers. Coal goes through a number of physical processes, sorting, but then they go through pulverizers. They are extremely hard carbon steel made of that, and it breaks coal particles in around between 20 to 40 micron size. It has to be very fine because it has to be injected together with the air into the combustion chamber. I want you to pay attention to here what kind of temperature range. Stable fireball in the furnace coming through various injectors, and the optimum temperature of operating pulverized coal furnace is between 1500 to 1700 Celsius. Okay, and as a result, you have nitrogen oxidation which is abundant. You will ask a question: why there's so much nitrogen oxides in the form of NO2, and we call them NOx, NOx. If you look at proximate analysis of a coal, you will notice that there is some nitrogen, but that's not the nitrogen that gives us nitrogen oxides. At this higher temperature, you may check in your textbooks or you may check with your professor. Something's called the Zeldovich reaction, which is the fixation of atmospheric nitrogen that is released, and that nitrogen reacts with oxygen to give us a lot of nitrogen oxides. Then, what is the problem with nitrogen oxide? Same thing you will ask with sulfur oxides. As they are being released, of course, the hot gases are cooled as it pushes out of the stack, and when it reaches a cooler level, together with the moisture in them, they become liquid. So come back to Earth in the form of nitric acid or sulfuric acid. That is the problem with having a lot of nitrogen oxide. Not just with this, it applies. Same thing with automobile engines, especially with very high compression ratios, high temperatures. Then forces us to use catalytic converters either for cars or for power plants. So this is something to keep in mind that will justify why then fluidized beds will be preferred over pulverized coal-fired plants. You may remember from yesterday that I said this was one of my first tasks in India, to come to India and help. Partner was the Bharat Heavy Technologies to convert those very bad polluting primitive pulverized systems to CFBs. So if you compare them, that fluidized bed is an alternative. We have an efficient combustion system. You have a much broader range of fuels. You can burn in fluidized beds. Operates at lower temperature. Again, it's a big advantage, especially from NOx perspective, and it also have as an integrated sulfur capture in a combustion chamber. What does this mean? You will see in a minute. In any other system, pulverized system, sulfur oxides occur. They're formed, and unless you have a flue gas desulfurization system above your plant, it's released in the atmosphere. In a fluidized bed, by using sorbents, we prevent sulfur oxides from happening in the first place. So we don't need to clean it because it doesn't form. So again, to review, the Q features is the fuel flexibility, that you can burn coal, biomass, or waste materials. More complete combustion because of one of the things is higher residence time and a high thermal efficiency. As I said, captures NOx and SOx, and heat recovery is much higher in this case. Here is, these are two existing industrial boilers. One is a bubbling bed. This is the bubbling bed part. This is solids recovery, heat recovery part, but also part of return system. Whereas this is the CFB. This is our riser circulating bed, and this is a cyclone that captures and recirculation happens here. And of course, a lot of heat recovery takes place here from the hot gases. We have, as I mentioned, three primary designs. It could be a bubbling bed, it could be a circulating bed, and it could be a pressurized fluidized bed. We're not going to spend a lot of time on pressurized fluidized bed. There are still a lot of research taking place to better understand a lot of things. But if it's pressurized, then you can use it in combination. Part of it as a combustor, part of it as a gasifier. Then, since it's pressurized, it can be connected to gas turbines, the pressurized gas, whereas the steam could be connected to a steam turbine. So much higher efficiency, but of course a lot more expensive to build and a lot more expensive to operate. We're not going to spend a lot of time on the pressurized fluidized beds because a time limitation, and second, it's still in the development stage. Again, we know most about bubbling beds. I Most of my designs of the bubbling beds, they were for biomass applications, but mostly for gasification type. If we I wanted to, some of my bubbling bed designs for simply for incineration purposes, so that waste or some agricultural biomass that could not be gasified could be burned to get rid of. So, principles of operation in these: find solid material like sand or coal. You put in a container, high pressure air. We blow it, we fluidize it, and it achieves a fluid-like state. And of course, we enhance efficiency and use it for various types of fuels. So I mentioned that again. I repeat, this is one of the design considerations. These are all approximate. These are all based on experience. You use 5% coal to 95% inert bed material. Then in this case, it could be ash or sand. And we are talking about steady state operations around here. So again, lower temperatures than pulverized coal furnace. And let's talk about sulfur emissions. Okay. Let me see if I'll go here. You see in this diagram, you have coal here being fed, and then you have limestone here mixed at a certain ratio into the combustion chamber here. Okay, this is a CFB. Now I go back. I should remind you, one of the critical advantages is in fluidized bed combustion, there is no need for pulverizers. Pulverizers are very expensive. They have to be maintained regularly because they are constantly grinding coal particles, and then they have to be fixed, replaced, and all of those. And they consume a lot of energy in doing that. There's no need for pulverizers in fluidized beds because the particle size is much larger, as we will touch. Okay, but let's go to the emission control and when it comes to sulfur. So we use limestone. What is limestone? Limestone is calcium carbonate. Okay, calcium carbonate does not directly interact with sulfur oxides. You have to calcinate it first, and calcination takes place under high temperature, a certain temperature range. That becomes calcium oxides, which unfortunately releases carbon dioxide in addition. So it has to be, if you examine a limestone particle under a scan electron microscope, you will see a really porous structure within it. The more porous it is, the higher the capture efficiency because it has a lot more surface area. It's not just around the particle, it's within the particle that gases interact with. Anyway, calcium oxide and sulfur dioxide, they react, given calcium sulfate, which is a solid material now, which can be extracted from the bed. Okay, this is the beauty of being able to do this. You cannot use this in pulverized system A because of a very high temperature, because of the size, and because of the short residence times. Okay, why is the temperature? If the temperature is above a certain level here, you basically bake the calcium oxide particles, and then you don't get the benefit, the porous structure. And it's like you bake it, it's just the surface that is in contact with it. So um, again, when it comes to heat capture, I touched on it yesterday. Boiler pipes can be placed within the bed with refractory preferred, but if you don't do this, you will encounter pipe erosion because of constant impact of solid particles on pipes. So we had a look at this before. So you have basically cold preparation here. It goes through some sort of, after it is mined and brought to the site, it goes through a crusher, but crusher is not the same as pulverizer, much larger size, and it also eliminates some other non-cold particles. There could be some metals in there, and it goes through magnetic separators. And here you have coal being fed. As I said, at a given ratio, limestone particles are introduced. Now, the mixture, of course, this is utilized, is pushed in there pneumatically, and then you have your a boiler here, and provide the primary air, and then secondary air for again, we talked about the secondary air to provide the kind of complete combustion here. This is operating under fast fluidization regime. That means all the solid particles are entrained out of the bed. They're captured, cyclones, and then returned. That's why it's a circulating bed. And then the rest is part of the steam power plant operates. Okay. Uh, so you have to have higher fluidization velocities. The other thing I should mention, okay, which is a disadvantage to pulverized boilers. So in a combustion application, um, you need to determine, here is my fuel. In my fuel, I have this much carbon, I have this much hydrogen. These are the main combustibles, okay? And you calculate your stoichiometric air requirement. Then to ensure more complete, stoichiometric amount is a theoretical amount. So to ensure complete combustion, you add more air than the stoichiometric amount. With pulverized systems, because of very high surface area ratio, you don't need to use a lot of excess air, because excess air, as the name implies, is just excess air. And even though it promotes complete combustion, it is lost through the stack, and it carries with it a lot of thermal mass. You can capture some of that, but only at certain level. Otherwise, you'll be condensing the flue gas, and if it's condensed in a liquid form, it will destroy the stack and everything under it, because it will come down in the form of acids, as I mentioned. So in fluidized beds, you have to have much higher excess air, because of the mixing process is not as rigorous, as violent as it is in pulverized systems. So this is a disadvantage. And nevertheless, this is the particle size range, and it is still efficient, because it provides, as you can see here, much longer residence times than PCs. If there is unburned carbon here escaping, we capture it back through cyclone until it becomes ash, and it's an ash particle that's lighter, and we can separate it much easier through separators. And another beauty here, just pay attention to this, 90 to 95% sulfur removal from coal. If you ever to design or take part in designing a power plant, you will see that when you use especially high sulfur coal, and of course nowadays you cannot not use a flue gas desulfurizer, they can be as expensive as the total plant. They are very expensive, especially if you're added on to an existing plant. So the advantage of this limestone is very cheap. Limestone is very cheap, and also the beauty of it, when you capture sulfurs, it's not in gaseous form. It is captured as calcium sulfate, which is in. Hey, are we doing okay? I hope so. I can't see you, so I'm assuming we're doing okay. So, what is next then? How are we? Who is using this? A lot of countries, especially even though this is developed in late 1980s, we had a number of demonstration plans in the 90s, and a lot of utilities started using this, especially in countries like the US, Canada, India, China. It is used significantly, and so various sizes of power plants, not as large because of the throughput ratio, but the one that I was involved in design was 165 megawatt electric plant that is still in operation. Let's again, we talked about efficiency. In this case, we use a fluidized bed. You have total overall maximum efficiency of the plant at around 43%, which is ideal, better than PCs. But if PCs are supercritical, again, you should know what supercritical boiler is, and then it could be higher. Emissions are a lot more favorable in this case, and the fuel flexibility is superior when you are burning a variety of low-grade fuels, especially. Okay. Um, I so far I kept talking about power generation, uh, that you use coal, and sometimes you co-fire coal with other fuels. Co-firing means you mix, let's say, coal with biomass, or there is something called, for example, petroleum coke. It is the sludge after the catalytic cracking. You can't burn it by itself. It can contain a lot of nasty stuff, but you mix it with coal. So depending on the application, you can mix it with a lot of things. So it's called co-firing. But it is ideal, especially if you have a large amounts of municipal waste, and the only way to get rid of this is through incineration. Then you can mix it with coal and burn it in CFBs. All right. What are the challenges when you consider, again, like the room you're in? Okay, the size of the room could be the plenum chamber of a bed. It's that size. So to to achieve a proper fluidization in such a geometry, large geometry, is extremely difficult. And the graph, the schematic I showed you, it had a partition in it, which divided the bed into two to ease that mixing or better fluidization. Stability of combustion becomes an issue, especially if you have slugs being formed, which is possible, or the agglomeration of ash. If the ash is at a higher temperature and it is that temperature is, if not, it is not well controlled, ash particles become soft. When they are soft, when they touch each other, they start agglomerating, and when you have those big agglomerates, they result in defluidization of the bed. So when you have a bunch of them, the drag force then cannot overcome the gravity force. They start sinking, and then you lost the bed. You lost the bed. You can even destroy the whole reactor. Bad material handling, again, is complex. It has to be sure that is properly fed to the bed. So these are some of the operational challenges that you should be aware of if you're designing and operating such a system. It's just quickly, it shows you again the operational or design history of, starting in, I mentioned the Winkler process, but very quickly, many countries, it's been adopted and successfully used. So next thing is, I'm going to go through this a little quickly, and part of this will be, as I'm going to use it as an example, tutorial example for you to see how we use these as part of our design of a system. So fuel preparation, as I said, is a challenge, is essential for a successful and efficient operation of combustor. Key processes that we need to make sure that they're optimized. Sizing is important. Even though I said a lot of they're versatile system, flexible, nevertheless, the more uniform the size is, the better, the more uniform mixing and fluidization will become. In a lot of cases, drying is important. Fuel comes from various sources, and they come with different levels of moisture. We promote a little bit of moisture, but not a lot, because nevertheless, you'll use the exothermic energy of your system in order to evaporate the fuel or moisture, bring it to 100 Celsius and evaporate it out of the fuel. We want it to evaporate, but because as it evaporates, it opens up the pores inside the fuel and allowing for oxygen penetration in there. But when you have a lot of it, it remains there too long, and it inhibits oxygen penetration in this case. So drying is important. And as I said, separation of non-combustible materials is important before it's fed into the side. Sizing, I mentioned already, but we can use up to even like 25 millimeters. 25 millimeters is like 2.5 centimeters. This is huge advantage compared to pulverized systems. And drying is itself is an integral and essential part of fuel preparation. So to summarize, separation of non-combustibles, fuel preparation of different fuels, and then we will see, you'll have to determine, depending on the amounts, on this impact on combustion efficiency. We already talked about this. Let me just talk about on the design considerations. So to accommodate fuel flexibility, our system, the CFB system, must have adaptable combustor designs. Robust fuel feeding system, that means it is adaptable when you have different types of fuel coming, and one day it's pure coal, the next day it is mixed with municipal waste, and also you have to have a proper emission control system to be able to adjust temperature, air, and also sorbent amounts. Okay. This is a very useful chart that will give us a good understanding of what kind of fuel we should use that will give us the amount of calorific value. At the end of the day, one of your key objectives is per unit mass of fuel, how much heat you will extract from this reactor that will be converted into high pressure, high temperature steam. You have to calculate that amount so that you will know exactly how much electricity you're going to produce. So this chart is very helpful to figure out which ones are part of the standard design, which ones we don't have enough operational experience, and you will need more probably pilot scale tests before you can use it in a fluid bed. Okay, so we talked about this as well. I'm also watching the time. Efficiency in, as I said, is important. Needless, I'm sure that you know these concepts, but let me remind you again. When we talk about efficiency, first is the combustion efficiency. Combustion efficiency, how much of the fuel you have converted into a thermal energy. So how much of the chemical energy has been now converted into a thermal energy. That is out of combustion efficiency. So as I said, it's very high in a fluidized bed. And then you have the boiler efficiency, and the boiler efficiency, how much of that thermal energy you've been able to transfer to the boiler or in the form of steam. Again, it depends on heat transfer surfaces. I'm assuming that you're able to see me when I show you something object. So when you have this tube, this is a heat transfer surface, water is going here or low pressure steam and coming out as steam or high pressure steam. When this is in an environment that is very dirty, you have a lot of ash particles, and they are at a higher temperature than this one. They're coming and hitting the surface. After a while, you have slack formations or condensation of hydrocarbons that form soot over this. So in some systems, for example, PC systems, you have to blow steam over these to remove that coating. Otherwise, it prohibits, it prevents heat transfer. In fluidized bed system, the advantage of if you have sand particles constantly, it breaks off that slack over it. So it promotes better heat transfer, but at the same time, if you have a lot of contact, then erodes the surface and erupts the heat transfer tubes. Okay. So with that, I was talking about efficiency. So we talked about boiler efficiency could be high, but overall thermal efficiency of the plant, because of what I showed you in the Carnot cycle example, because you have to condense the low quality, low pressure steam, then you lose a a lot of the energy. Therefore, your overall thermal efficiency of your plant is very much limited. Again, combustion efficiency, as I said, we can achieve up to 99% combustion efficiency in CFBs because we keep, if you have unburned carbon escaping the bed, you'll bring it back and then burn it to smither until it is a fine and light ash particle. Okay, I explained these, improving efficiency. We can do all kinds of things in order to reheat cycles, economizers, and everything, but this is beyond our scope. But to give you, again, a good comparison, CFBs, you can use it for these kind of fuels compared to one bubbling fluidized bed application, and you have some thermal efficiencies. These are from operating systems, but I did not include the source did not include which ones it is because of the confidentiality. Okay, so emission controls, as I mentioned, it is crucial that we control three sources of emission. Talked about sulfur oxides. Why it is, if you don't control it, it will come back in the form of sulfuric acid, horrible for the environment. It destroys forests and vegetation and everything, but it also destroys the power plant as well. Nitrous oxides, the same effect in the form of nitric acids. And the third one is particulates. In power plant terminology, it's called SOx, NOx, and ROx, as it refers to the particulates. So particulates, there is no, it's a completely physical process. You have to ensure that you have, in addition to cyclones, you have electrostatic precipitators and filters so that no particulate matter escapes into the environment. If it escapes, everybody ends up breathing it, or it accumulates on everything, including vegetation. So if you want to design and operate in these modern days a solid fuel fired system, you have to ensure the regulators that you have completely control these three pollutants. Of course, this is beyond our scope, but then you have to have other proofs of how you control carbon dioxide, whether you capture it or not. That's a completely different subject. But in our case, ironically, the objective is to maximize the amount of carbon dioxide while minimizing the amount of carbon monoxide leaving the power plant. Okay, we talked about this particulate matter. Yes. So let's touch a little bit on the biomass. So far, we talked about mostly about coal. Now let's go to biomass as our fuel. So, as I said, biomass will come from various sources, whether it's agricultural crop waste. For example, you grow corn. A lot of the parts that are not used, it comes back as waste. If you, let's say, grow rice, very much like in India, and you're all familiar with, you have to dehusk the rice. What do you do with the husk? It's a byproduct, it's a biomass, or simply waste from a number of municipalities, including if you have a sewage treatment plant, the sewage, the sludge, they are all biomasses, and they come in with high moisture ratios. So every biomass combustor will have to have a drying either within the bed or adjacent to the bed, a dryer before it comes in there. So you have fresh biomass, it enters, you have to dry to a level, remove the moisture, for which you're going to spend energy. Uh, the polymer is the gauges matter. Unless or heating goes, they will leave the and char, all the part much faster than the char, and then nevertheless you have oxidation of carbon that results in the form of carbon dioxide, and oxidation of hydrogen that results in the form of water vapor leaving here. Of course, the net effect here, this is an exothermic reaction. Heat is released, heat is captured, and it is utilized in one form or another. So let's go through this. This is part of our exercise to go step by step. This we are designing is still um, drying. We're going to talk about later on specifically about fluidized bed drying. So the drying process here is the physical aspect of drying. It could be fluidized bed, or it could be just an external dryer, but nevertheless, it requires energy input. You have to incorporate this into your calculations, that you have to predict or determine. There are ways, of course, to do a moisture analysis of your fuel. Then you will know that part of your energy that will be released from the fuel will be taxed to evaporate that fuel, the moisture above at 100 Celsius evaporation temperature. If you don't dry the fuel properly, it will inhibit combustion. It will result in premature combustion, and because your fuel is only for so long in the bed, it will. If it takes too long for it to release its moisture and then devolatilize and then burn, then it will occupy a lot of space and time, then your throughput will not be very high. So those are important factors to consider when drying. So there are various ways to predict that through modeling. The hint sink approach is very easy. It's limited by heat transfer, and all the heat is used to evaporate. Then straightforward one is a zero order reaction model of Arrhenius that I prefer using it over the other two. An equilibrium approach is assuming the water vapor and liquid moisture are in equilibrium within the particle. So which is more accurate, but Arrhenius is a lot more straightforward. Uh, and it just gives a little bit more detail in how we use this. Hint sink approach, useful for fluidized beds where internal heat transfer resistances are significant. Nevertheless, for numerical modeling, as I said, this gives us a linear approach, which I prefer because it reduces computational time, and calculations are more straightforward. Let's pass these. We will talk about. So, a little bit more better understanding, which will be helpful for our lecture tomorrow or the day after. So, in a particle, when you're drying it, as the moisture evaporates, it shrinks. Okay. So, how much do you need to do this? This is your temperature moisture diagram. So here you're increasing the temperature. It moisture remains because it has to come to that boiling point, evaporation point, after which it starts dropping, and you reach a point where you're no longer able to remove the surface moisture because the rest is diffusion controlled. When it's diffusion controlled, it is independent of temperature, as you can see. Regardless of how much you increase temperature, it flattens out. So this is the point that you need to model. This is why we're trying to model. This is the point that you need to determine at which point that you no longer you need to dry it, leave it, because you have removed this part. Then the rest will be diffusion controlled, and as I said, in some cases it will enhance combustion, but nevertheless it slows down the burning rate. Yeah, so different equations as to how you determine the amount of moisture removed, and all of those. Let me pass these. Let's get to the second stage, devolatilization. Means release of the volatile matter out of the fuel. Okay, so those volatile matters, okay, is the gaseous ones, and the burning it burns much faster, and it usually with biomass, it can be up to 80% of the total weight of the material. So it's significant. Why am I saying this? Because you have to understand that when the volatile matter is burned, it is much faster. Therefore, a lot of heat is released at that time. You need to be able to capture it. The remainder is char particles, and char is the solid part, which burns much slower. And this is the part, if you're using a CFB, you have to ensure that it is recirculated. So you have to configure your heat transfer surfaces in a way that it is able to capture the heat from the combustion of the volatile matter and also heat release from the combustion of char, which is in a much larger, happens in a much larger time frame. So this is for that part. Then how do you uh, control the kinetics? How do you determine the kinetics of biomass and pyrolysis, of course, initially? In any biomass, it is not a homogeneous thing. It's not just this or that. It is quite heterogeneous and includes natural polymers, cellulose, hemicellulose, and lignin, and they each decompose differently. Okay, burn differently. So in our treatment, however, simplest approach is to say, to heck with it. We assume that it's homogeneous and everything happens at the same time. So you use Shafizadeh and Chin's model that you have three parallel, but they're first order reactions, okay? And then they're transforming, if this is, for example, a wood particle, transforming it into a gas char. And of course, a consequence of this is tar, which is, I haven't mentioned it so far, one of the biggest disadvantages of biomass that you have to, especially if you're gasifying it. Combustion is at high temperature, we don't need to worry about, but if it's part of the pyrolysis problem, tars are formed, you make sure that it is burned. Anyway, three first order reactions, you do this. You use the global constant for overall fuel conversion, and you use the Blassi's activation energy within the temperature range of what you're doing. Okay. Uh, yeah, we touched on the volatilization, and I have 1 minute left for this. So I'm gonna stop here. I'm gonna finish this, but we have a little bit more time in the form of a tutorial, which I'm going to use it to finish this one and to touch on the hydrodynamics part. So let's take like we did last night, 2 3 minutes of break, and then let's restart. You go stretch your legs. I'll do the same. Washroom break, water, and then we'll come back in. Is 5 minutes okay? Okay. Thank you. Okay, thank you. All right, welcome back. So we were talking about combustion of volatiles, and obviously, when we say a volatile matter, it's predominantly carbon monoxide. Comes from the pyrolysis part or incomplete combustion of carbon, and of course, hydrogen. There are some others, but these are the two main combustibles. And it represents, as I mentioned, a significant portion between 50 to 60% of the total energy released. In some cases, it could be even more during biomass combustion. Needless to say, uh, when you are burning something in your furnace or a combustor, you will have it analyzed in the lab. So you will know exactly the chemical composition of that fuel so that your calculations will be very accurate. Um, and the reactions, of course, pyrolysis and volatile combustion, which will follow pyrolysis, basically at the end, you see carbon monoxide. Where is my cursor? It's here. Carbon monoxide reacting with half an oxygen, of course, giving carbon dioxide, hydrogen, giving water vapor. Basically, hydrocarbons, when they react with oxygen, they will give you carbon dioxide, theoretically, of course, and hydrogen and water vapor. There will always be some carbon monoxide present, escaping unreacted because of the nature of the reactor. So when you look at it and a fluidized bed part of it, um, where are the exact, remember I said you have to determine your locations of your heat transfer surfaces precisely. So bubbles, the volatiles form bubbles, okay? They will be in the bubbles because they are part of the process in bubbling bed. Around biomass particles, when you have bubbles, they're not reacting directly with the fuel, they will rise to the bed surface. So within the bed, mixing is poor because the bubbles entrap these volatiles. When they're entrapped in there, they're not mixing to the bed and burning. Okay, so major combustion will take place as the bubbles burst and mix with oxygen. So this is just for the volatile matter, okay? That means you have the bed, dense bed, the freeboard, then you make sure that you have proper heat transfer surfaces in the freeboard to capture the heat that is released from the combustion of volatile matter, okay? With char, it's a different story. So what are the factors affecting volatile combustion? Temperature. The higher the temperature, better the combustion rate, but you know the limitations of temperature. Gas velocity, again, as I mentioned, it promotes better mixing, but it costs you. And bad material, make sure the inert particles, the more inert particles, non-combustible particles you have, the more tax you will pay in the form of heat loss and, of course, ignition delay. And but you can also add some other materials that can enhance combustion in addition to your fuel. Okay. Um, what are the challenges? Incomplete combustion, which is usually the case, as I said, will end up in carbon monoxide emission. You improve mixing. So to improve mixing, you either put static mixtures or even forced, but they all, if you have static mixtures, it will nevertheless, it's an additional resistance, and static mixtures, they can cause fouling and other challenges. So it adds to the cost, but nevertheless, to achieve uh, better mixing, you need to either use more secondary air or use static or dynamic mixtures to promote mixing. Heat distribution is uneven. If it's this is caused by hotspots, and if you're not able to remove heat uniformly, hot spots that may affect not only efficiency but also the furnace life by causing weak points. Again, make sure that your bed design will have uniform heat removal. And we talked about kinetics and other things. Now let's turn our attention to char combustion. Char is what is left as fuel after the volatiles are released. It's much slower, it's combustion. This is the longest step, and you have to, which will determine, of course, your solid recirculation as well as the reactor side for a very simple reason, ensuring that you have long enough residence time. Okay. Uh, this is a fundamental thing for any combustor, okay? To achieve a maximum combustion efficiencies, you have to pay attention to what we call 3 T's: time, temperature, and turbulence. The higher they are, the higher the efficiency. But as I said, you cannot keep it too long there, otherwise you're preventing fresh particles coming in there, and the temperature cannot be too high. Then you lose the advantage of a fluidized bed. Then the turbulence, you have to pay for. Turbulence is good, but you have to pay for it in the form of more air. So but if you have them, then you will achieve them. Then these are the, again, basic reactions. Now, carbon reacts with oxygen to give carbon dioxide. The steps are, first it's carbon monoxide, then carbon reacts with carbon dioxide as well, or it reverses into carbon monoxide through a Baudard reaction, and then carbon and water. This is the water gas reaction, water ship reaction that releases hydrogen. So this is a continuous process that is taking place. Okay. Leave that too. And yeah, we talked enough about char combustion. Okay. This is all I wanted to share with you. I want to talk about within our limited time about the application of fluidized beds for the combustion of solid fuels, which are predominantly coal or biomass. I hope you had a very basic idea about the process, basic idea about operation, and basic idea about what should be considered for a design. There is no way that within how much information I was able to give you and you have in your possession, you can go and design a fluidized bed combustor, but at least you know where to begin, you know how to do this. People who do these kind of things, they are, of course, they have amassed many, many years of knowledge and experience, but nevertheless, we just scraped the surface, and there is a lot more depth under the surface. Okay. Uh, I stop here and I wait to see if there are any questions. If not, I have one example I wanna go over with you, and that will finish this class for me for today. Okay. So, any questions? Yes. Not fully, but I could only capture half of it. I think it just went in and out. So if you could just speak to the microphone so I can hear better. Yes, much better. Yes. Mm, yeah. Yes. So very good question. Both options are possible. In some cases, we use the fluidized bed as a combustor, but everything I say is steady state. When you start from cold, it's a different operation. You will need to have a secondary fuel like propane or natural gas or liquid to bring the bed to the operation temperature, at which point you can start feeding the fuel. Okay. So in one scenario, it's just a combustor. You are feeding a already dried fuel into it, and you're extracting some of the energy of this, giving it to an external dryer, removing the moisture up to a certain level of the fuel and feeding it into the fluidized bed. In the second option, the dry air is already it's within the bed. You adjust the bed size accordingly to make sure that you have enough time to dry the fuel that goes into. So you probably, like, for example, you can partition the bed, okay, and as it dries, it weighs less, and then it goes over the partition into the combustion chamber. Okay, so these are all possible designs, but very good question. It's up to you, and it depends on the fuel type. Sometimes when the moisture level is really, really high, you want to dry it externally. Okay, even you may use mechanical separators like centrifugal that you could push the moisture out, and whatever is in there, then you can use it, remove it thermally. Okay. So if you're using a bubbling bed, it's usually batch, okay? Unless you add another portion to it, but it's usually that because um, the ash removal is, if you're not successfully able to remove because they're lighter and you can capture whatever, but if they're slagging, they become heavier and you cannot drain it under the bed. It's a batch operation, but if it's a CFB, it's definitely a continuous operation. Okay. Hi. What say it again? So inert part. So as I said, what big advantage of a fluidized bed is it has a very large thermal mass. That thermal mass is deposited in inert particles. So you have to have that inert particles, either it's sand or ash, whatever, so that it provides you the activation energy of the fuel, without which, if you don't have it, like the bed in this case is the spark plug of your car engine. Okay, so the inert particles, they provide that activation energy for the fuel to combust. Okay, any more? Hi. It is important to maintain it, not only maintain it, but keep it uniform if you want to have uniform combustion across the bed and also uniform heat transfer. If it's not uniform, you will end up like in your heat transfer surface, unequal distribution of heat, which may result in a lot of problems and inefficiencies. So it is very important to ensure that it is uniform, and for it to be uniform, you have to provide a very good mixing. This is one of the key elements of both design and operation of a successful fluid bed. So let me ask you, Professor, so have they seen an operating fluidized bed? Have they been to the lab yet to see how a fluid bed operates and how the bubbles interact with particles and all of those? Have they seen an operational fluid bed? Okay, but they have seen at least like a transparent fluid bed and bubble formation and all of those. Okay, good. All right. Thank you. Well, good morning to you. For me, it's what time is it? It's it's almost midnight. But thank you. I will remember you wishing me good morning tomorrow morning, okay? Very good. Overall, yes, there is a ratio, and in overall, when we calculate the plant overall efficiency of the plant, all the auxiliary powers, okay, they are incorporated into it. So, and they are nevertheless, auxiliary power consumption is quite small compared to the enormous heat loss through the condenser. So, yes, as far as environmental benefits go, I can tell you how, like, I've done a lot of techno-economic analyses. With the exception of carbon dioxide removal, it is still the most economic, technologically superior and economic solution when it comes to solid fuel combustion. Okay, but uh, if you have to consider carbon dioxide removal, then it applies to all fossil fuel, whether it's a natural gas, whether it's an oil fired, whether it's coal fired, they all release carbon dioxide. But from my former colleague, good friend, Professor Basu's book. It's simple, but please don't mind my handwriting. And my handwriting, I wrote this on my tablet, so it's a bit, but I hope you can read it. So I said minimum fluidization velocity calculation in a bubbling fluidized bed. And how do we do this? So the input, I have to tell you what kind of bed material I use. In this case, it is sand. And my average particle size is 30 micrometers, okay? And then, of course, you can easily find the density of particle as that's around 2,600 kilograms per cubic meters. And the bed is square cross section and 0.203 meters by 0.203 meters, okay? So this is the geometry, these are the physical parameters, okay? So I'm asking you in two cases, one case at ambient temperature of 27 Celsius, and the other one is at an operating temperature of 825 Celsius, in which case I give you the physical, the gas density and viscosity at ambient temperature, and at 825. You can easily, again, find these from tables, physical property tables. Okay, so under these conditions, I want to find the minimum fluidization velocity and minimum bubbling velocity and terminal velocity of particles. Okay. To be able to do this, the first thing we will need to do, as we talked about it yesterday, we need to determine which particle group does the particle of the given diameter I gave you, it belongs to. So you remember the chart? I said this is the Geldart classification, and you have the properties there. From that chart, you will realize that for a given particle size and density, this belongs to the group B particles, okay? And with that, then to calculate minimum fluidization, I said terminal, but it should be minimum. I have two ranges of Reynolds number. One, if Reynolds number is less than 0.4, we use the formula. They are all derived from basic formulas, and also used, of course, the constants come from correlations from the experiments. And if it's between 0.4 and 500, it's a very large range, but we use the second formula. In this case, I calculated the Reynolds number. I gave you the formula yesterday, and I found it to be almost 45. And if it's 45, it is within the range of 0.4 and 500. I use the second equation. When I use this, I find the velocity. One at 27 as 2.37, and the other one is 2.72. I'm sorry, this is the UT. So from there, this is again the Reynolds number definition, and this is further through correlations, experimental data by somebody I mentioned yesterday, late Professor John Grace. This is one of the most critical contributions that it is translated into this form, in which C1 is 27.2 and C2 is 0.0408. When you put those in there, and the Archimedes number, it's defined as this one. And when you plug them in, you find the Archimedes number is 2268, which gives us a Reynolds number at minimum fluidization at 1.65. This is for the gas, okay? And therefore, you have their ambient conditions, a minimum fluidization velocity of 0.087 at 825 because of course, different physical properties. It is further reduced. So even at lower velocity, you have achieved minimum fluidization. Okay, that means at these velocities, you no longer have a fixed bed. It will start fluidizing. Since this is a group B particle, minimum bubbling is the same as minimum fluidization. So as soon as the bed is fluidized, then the bubbles will form. Therefore, group B particles are difficult to handle. So if you can, don't. The easiest one is to use group D particles. Oh, I don't know what happened to my, sorry, just 1 second. Okay, I think, yeah, I calculated the turbulent before minimum fluidization, but just simply, I wanted to show you that uh, given, and as I said, there's a lot of, am I still there? Can you see me? Oh, I need to stop sharing. That's why. Okay, I don't know what I did, but I everything got mixed up here. You can still hear me, right? Okay, so this was an example of very simple hydrodynamic calculation that you can start from there, always determine the particle, which classification it fits into. And then from there on, there are large number of correlations, but it's the safest to use the Grace 1982 correlations, calculate your Reynolds number, Archimedes number, and all of those. And from there on, you can calculate all the physical parameters that you need, bed expansion to transport disengagement height, and all of those for a given mass of or cross section of bed. I'm gonna stop here because I'm out of gas, and I will recuperate again for our tomorrow lecture, which I think will be about on gasification. There are no other questions. I wish you a good, productive morning. And please also, how about this? Before we start tomorrow, think of anything that you want me to go over again before we do gasification, okay? All right. I will say goodbye now. Until tomorrow. Okay.
हेलो हेलो।
नहीं लिया कैपिटल।
अच्छा ये मैनेज योर क्लास ज्वाइन मीटिंग इन जनरल ज्वाइन है तो लेकिन दो दो आ रहा है।
पुराना वाला कुछ होगा ना।
7 मिनट्स हो गया स्टार्ट।
दो दो मत चालू करो, दो दो चालू करने से दिक्कत होगी। दो मीटिंग्स चल रहे हैं। उसको ऐड कर देना, उसको रिमूव करके इसमें ज़्यादा लोग हैं।
हाँ
उसको इसमें
अभी कौन सा वाला चल रहा है?
ये 10 लोग हैं इसमें। हाँ
हाँ हाँ हेलो अब हाँ ठीक है।
पीपीटी भी ओपन करेंगे। पीपीटी भी ओपन करेंगे।
पीपीटी मिनिमाइज करना पड़ेगा। अच्छा पीपीटी वीडियो बीच पे मुझे ओपन भी करना है।
पीपीटी भी वीडियो चलाना है।
हाँ वीडियो भी बीच में चलाना होगा तो ये स्क्रीन मिनिमाइज करके करूँगा। हाँ
ऑडियो इंपोर्ट करना पड़ेगा। जब शेयर पे जाएंगे तो इंक्लूड सिस्टम पे करना पड़ेगा।
नहीं ऑडियो नहीं चाहिए।
वीडियो प्ले
हाँ खाली वीडियो ऑडियो नहीं चाहिए। यार स्क्रीन करना स्क्रीन कर दीजिए सर।
पूरा पूरा स्क्रीन है।
ना विंडोज करना नहीं स्क्रीन करने से उधर प्ले करूँगा तो होगा ना।
हो जाएगा सर। अच्छा ठीक है चलिए। नहीं इनका माइक ऑन करेगा फिर तो वो होगा इको होगा।
हाँ उधर होने से क्या होगा क्योंकि मैं प्रेजेंट कर रहा हूँ ना।
हो गया स्क्रीन आपका शेयर।
the topic hydrodynamics of gas, liquid, solid, three-phase fluidized bed. So a three-phase fluidized bed consists of three phases. One is gas phase, second is the liquid phase, and third is the solid phase. Usually in the fluidized bed, as you know, a bed of solid particles comes to a state of suspension by the flow of the fluid. The fluid may be gas, liquid, or it may be together gas and liquid. When it is two fluids are there, gas and liquid, then the fluidized bed is gas, liquid, solid fluidized bed. The outline of my presentation is introduction, classification of gas, liquid, solid reactors. Although my main discussion will be on gas, liquid, solid fluidized bed, but what are different types of gas, liquid, solid reactors, that also we will discuss. Then modes of operation of the gas, liquid, solid fluidized bed, the flow regimes, experimental hydrodynamic study, and computational hydrodynamic study. Gas, liquid, fluidized beds are the most promising device for three-phase operations because of the intimate contact of the three fluid phases, gas, liquid, and solid. Many types of operations are carried out in this gas, liquid, solid fluidized bed. Because of vigorous mixing in this reactor is possible. So gas, liquid mass transfer, liquid, solid mass transfer, or it is gas, solid mass transfer, depending upon the type of fluidized bed, are possible in this gas, liquid, solid fluidized beds. And this gas, liquid, solid fluidized bed is widely used in chemical, petrochemical, and biochemical processing. Few of the examples are in the hydrotreating and conversion of heavy petroleum and synthetic crude, H-oil process, that is hydrogenation and hydro desulfurization of residual oil, in hydrocarbon cracking and reforming, oxidation of naphthalene to phthalic anhydride, that is a catalytic one, fluid catalytic cracking, as you know, FCC, which is common in petroleum industries, that is a catalytic type. Then another one, non-catalytic operations also, this gas, liquid, solid fluidized bed is used, that is coking of petroleum residues. Then H-coal process for coal liquefaction as a turbulent contact observer for flue gas desulfurization. It is used in many pharmaceuticals and mineral industries like penicillin production, etc. Then some physical operations, and in biochemical processes such as fermentation, aerobic and anaerobic wastewater treatment. The classification of gas, liquid, solid reactors. 2A, it is classified. One is the factors and the variations. So state of motion of solid particles, because three phases are present, gas, liquid, and solid, and solid is the first and foremost thing for the fluidized bed, because as per the definition of the fluidization, a bed of solid particles comes to a state of suspension by the upflow of either gas or liquid or solid. Gas or liquid, or the combination of gas and liquid. So the solid is having the importance. So state of motion of solid particles, either it is stationary or it is a slurry suspension with the mechanical agitation, slurry suspension without mechanical agitation, and fluidization. Then the types of operation, the liquid phase or the gas phase. So gas continuous, either it is, or liquid is either batch or continuous, solid is batch or continuous. relative flow direction of phases for continuous operation, gas and liquid, co-current upflow or co-current downflow, then counter current flow or cross current flow. Solid may be flowing in upward or a downward direction. The situation of phases, the gas is the continuous phase or discrete bubble form, gas might be moving in the bed. Liquid is continuous phase or in the form of film or in the form of droplets. Solid, either it is packed, slurry suspension, fluidization with either liquid or gas as a continuous phase. The classification of gas liquid solid reactors and the contactors based on the previous overall classification. One is the operation one, that is class 1, that is the packed bed. The type of reactor is the packed bed reactor. The operation for gas and liquid, then the continuous phase, operation for solid, particle size, force of solid suspension, gas liquid mass transfer, wall to bed heat transfer, fluid mixing and the process application. These are the classifications for the packed bed reactor. So column 1, as you see, it is the counter current, or concurrent upflow, concurrent downflow. Where the continuous phase, when the continuous phase is the gas, there is trickle flow, that means water or the liquid trickles down. And when the continuous phase is the liquid, the gas moves in the form of bubbles, dispersed bubble flow, or it is slug flow. Then operation of solid, solid is batch in packed bed. Once it is there in the bed, always it remains intact in the bed. The particle size normally used in the packed bed of size greater than 1 millimeter. The force of solid suspension is stationary. Gas liquid mass transfer, gas liquid phase controlling here, and the KLA, that is the mass transfer coefficient, liquid based on the liquid phase, that is 5 into 10 to the power minus 4 to 0.1 liter per second for the counter current operation, and for concurrent again it is up to 1 liter per second. Then wall bed heat transfer, poor for trickle flow and fair for dispersed bubble flow or slug flow. Fluid mixing is low fluid mixing is there in the packed bed. Process application, absorption, desorption, chemical absorption, gas liquid solid catalytic reaction, biochemical reaction. Then another type reactor in the class 1 is the packed bubble column, where the operation of gas and liquid is the counter current, concurrent upflow, internal liquid circulation. These are the classifications. And in the packed bubble column, continuous phase is the liquid, the operation is batch as far as the solid is concerned, and the particle size used is more than 10 millimeter. That means high wattage packing is there in the case of bubble column. The force for solid suspension, there is no suspension, solid is stationary. Liquid phase controlling here, KLA value 0.04 to 0.2, and wall to bed heat transfer is fair. Fluid mixing is the intermediate. Applications are chemical absorption, biochemical reactions, etc. Then operation class 2, the reactor type is the agitated vessel. Operation for gas and liquid is the cross current in agitated vessel. Continuous phase is the liquid. Operation for the solid is either it is batch or continuous. Particle size normally small particle size less than 0.1 millimeter. Force of solid suspension is mechanical agitation by the use of stirrer or such kind of device. Gas liquid mass transfer, liquid phase controlling, and a low, it is very low value to up to 0.8 it is, that is from 0.005 to 0.8. Wall to bed heat transfer is good. Fluid mixing is complete mixing of the fluid is there. Gas liquid solid catalytic reaction, biochemical reaction, these are the process applications. Operation class 3, gas sparged slurry reactor. The operation for gas and liquid phases, co-current, counter current, internal liquid circulation, external liquid circulation, and jet mixing. Here again the continuous phase is the liquid. Operation for solid is continuous flow of solid is there in this reactor. Particle size less than 0.2 millimeter. Force for solid suspension, mainly the gas. Gas actually impart the drag on the solid particles. Gas liquid mass transfer, liquid phase controlling, KLA value 0.005 to 0.3. Wall to bed heat transfer is good. Fluid mixing is very high. Process application, gas liquid solid catalytic reaction, chemical absorption, biochemical reaction, absorption adsorption processing. Then operation class 4, the type of reactor is a fluidized bed, spouted bed. Operation for gas and liquid, co-current upflow, counter current. The continuous phase is a liquid, gas. Okay, either liquid is continuous or gas is continuous. Operation for solid, it can be batch or it can be continuous. Particle size for co-current, particle size normally 0.2 to 8 millimeter. Liquid continuous, that is the turbulent contact observer, and a particle size 3 to 40 millimeter. Where the density of the solids, these are low density solid particles are used, 90 to 1200 kg per cubic meter. For gas continuous, that is turbulent contact observer is used. Force for solid suspension, liquid and gas, liquid continuous, mainly gas for gas continuous. So force of solid suspension, either it is the liquid or it is the gas, depending upon the flow rate of liquid or the gas. Gas liquid mass transfer, liquid phase controlling, the value 0.005 to 0.2. Wall to bed heat transfer, very good for the liquid continuous system. Fluid mixing, intermediate for fluidized bed, complete mixing for shallow spouted bed. Process applications, fluidized bed co-current system, gas liquid solid catalytic reaction, biochemical reaction, chemical absorption, counter current systems, biochemical reaction, turbulent contact observer, physical absorption, chemical absorption, particulate collection, cooling tower, and the spouted bed, it is co-current for the purpose of dissolution, gas liquid solid reaction, drying, granulation, and counter current systems similar to that of the turbulent contact observer. This is used. So these are the classification of different types of reactors. Then the mode of operation, although there are considerable similarities between the gas phase slurry column and a gas liquid solid fluidized bed, as we have seen, but there is distinct difference in operation exists between these two systems, sparged slurry column and the fluidized bed. As you see in the schematic here, the top one is this one is the slurry column and the bottom one is a fluidized bed. So the difference is based on the particle size, volumetric fraction of solids, cause of suspension of the particles. The bed expansion may be uniform, non-uniform in fluidized bed. The bubbles intensify the mixing of solid particles in fluidized bed. The solid particles in both systems can be operated in either a batch or a continuous mode. In slurry column, the solid particles are usually carried in and out by the liquid stream. As you see here, okay, the solid particles are entering to the system with the liquid that is in the form of slurry. Then after processing it is leaving. But in fluidized bed, the solid particles may be the batch ones, solid is not getting out from the system, or solid may get out from the system. Also externally we can charge the solids here. The solids we may charge in case of the fluidized bed. So in fluidized bed the solid particles are supplied or withdrawn independent of the liquid stream, whereas in a slurry column it is in the liquid suspension the solid particles enter into the vessel. According to the relative direction of the gas and the liquid flow, the modes of operation is divided into two types, co-current and counter current. So as my topic is the three-phase fluidization, gas, liquid, solid fluidization. So next we will see the classification of this gas, liquid, solid fluidization. Based on the modes of operation, it is co-current or counter current, and based on the contacting pattern between the particles and the surrounding liquid and gas, the classifications are like this. This is the taxonomy which was given by Epstein in his publication in 1981. The three-phase fluidization, either it is co-current or it is counter current. Again, the co-current, it is bubble flow or trickle flow. Bubble flow means liquid is continuous and gas moves in the form of bubbles, and in trickle flow your gas is continuous and liquid trickles down. That means just moves on the surface of the solids in the form of film. That is trickle flow. Again, bubble flow is classified into liquid supported solids or bubble supported solids. When the bubble size is very small, that means in the discrete bubble flow phase, the liquid supported solids are there, but in the coalesced bubble flow regime or slug flow regime, bubble supported solids are there. That means the gas bubbles impart force to the solids to make it suspended. And in counter current, again it is classified as a trickle flow, which is a turbulent bed conductor, and the bubble flow. Again, bubble flow means it is the liquid continuous, and in trickle flow gas continuous, liquid trickles down. Again, bubble flow in counter current classified as bubble supported solids and liquid supported solids. If it is liquid supported solids and counter flow operation is there, downward flow of the liquid, inverse three-phase fluidization we get, where low density solid particles are used. And if liquid is stationary, in between we have liquid stationary liquid, then only gas is moving. Then the gas bubbles will support the solid particles, so bubble supported solids we are getting in between. The mode 1A of the operation, it is the co-current fluidization with liquid as the continuous phase. As you see here, this is the mode 1A, liquid is the continuous. So both in the co-current flow in the upward direction, liquid and gas moving, and solid particles are there. Solid particles are in suspension, and the red color, the bubbles you see, these are the gas bubbles, and the liquid is the continuous phase. Mode 1B, co-current fluidization with gas as the continuous phase. Here you see the gas is the continuous phase, entire space is occupied by the gas, and solid particles are there, which is the green dots as you see, and there are few curved lines, small curved lines as you see, that way represents the flow of the liquid in the form of that is in the form of just films of fluid flowing over the solids. That means liquid trickles down. Then mode 2A, it is liquid in the downward flow and gas in the upward direction, that is the counter flow operation. Inverse three phase fluidization, the bed of solid particles are fluidized by downward liquid flow opposite to the net buoyant force on the particles. So here the particles are lighter than that of the liquid usually. So if the bed is occupied with the liquid and the solid particles are present, so the solid particles will float, and it will be attached to the top distributor. This is the distributor, top distributor plate. So it is in the floating condition, there is no fluidization. That means it is forming a fixed bed at the top. So when the liquid flow is there in the downward direction, because of the drag that the liquid imparts on the solid particles, those they are floating at the top of the liquid, then the solid particles are dragged down, move in the downward direction. So there is the suspension of the solids like this, and the gas is moving in the upward direction, and these are the gas bubbles, that is the red color, the bubbles as you see. Then if we liquid is in the downward direction and gas in the upward direction, counter flow, but gas is the continuous phase. In 2A, liquid is the continuous phase, inverse three phase fluidization, and in 2B, gas is the continuous phase, fluidization represented by turbulent contact absorber, TCA. An integrated bed of low density particles are fluidized by the upward flow of gas as the continuous phase. The vigorous movement of the weighted particle give rise to excellent gas liquid contact. So excellent gas liquid contact is possible in turbulent contact absorber. But as far as the use of different types of the modes of fluidization are there, the 1A is the most widely used type, followed by this 2B and 2A. So co-current gas liquid solid fluidized bed, this is generally referred as gas liquid fluidization, because solid, of course solid particles are always there, without that there is no fluidization. A schematic representation of an experimental setup for three phase fluidized bed is here. So suppose water is stored in a tank and water is pumped. Water is the liquid phase which is pumped into the vessel which contains solid particles, and the water flow or the liquid flow can be measured using rotameters or any other flow measuring devices. For data capture, rotameter is not good enough. Other flow measuring devices, differential pressure cell we can use. Then gas phase is air used here. So air compressor, the air is entering to the vessel, and the air flow rate is measured again using the rotameter for a laboratory setup. but this can also be measured using other flow meters. And the gas is dispersed to the vessel with one sparger. This is a sparger. So as both liquid and gas moves in the upward direction, impact the drag on the solid particles. So solid particles comes to a state of suspension. And these are the bubbles of the gas. So bed of solid particles expanded up to this, as you see. This is the black dot is the solid particle up to this. That means this is the three-phase region. Up to that, we consider the height of the fluidized bed, three-phase fluidized bed. Above that, there is a two-phase region where gas and liquid is present. At the top of the vessel, the gas leaves the liquid, and this part is nothing but the disengagement section, whereas this part is the gas liquid distributor section at the bottom, and the main fluidized bed, which is called as the reactor or the test section, is this much. So bottom there is a distributor section where gas and liquid distributes and mix together and enter to the vessel, and at the top of the bed there is a disengagement section where the gas phase escape the liquid. Then to measure the pressure drop across the bed, pressure drop represents the drag that is required to make the solids suspended. So that can be measured, the pressure drop can be measured using simple differential U-tube manometers, or any other pressure measuring instruments can also be used. So for a simplest setup, the pressure drop can be measured using the manometers. So as you see here, another schematic is here. The bubbles, as you see, so below the bubbles, wake is there. Wake means a low pressure region is created below the bubble. That is circulating fluid is there. So liquid and gas, as it enters and moves in the upward direction, liquid is taken out from the system here, and as you see here, liquid is drained, and again it is recirculated. It is going to the tank, and this is the this portion is the gas liquid solid fluidized bed portion, and above there is a two-phase region, gas and liquid. So a photographic view of a gas liquid solid fluidized bed is shown here. Solid particles, as you see, bigger size solid particles for a visual observation that is made. Rashig rings you see that is getting fluidized by the upward movement of the liquid and the gas, and this is hazy, as you see. It is not complete because of a small gas bubble, air bubbles are there in the bed, so it makes the bed hazy. Co-current gas liquid solid fluidized bed, the different types of flow regimes we come across depending upon the flow rate of the liquid and the gas phase. The liquid with the gas forms discrete bubbles which supports the particles. Bubble flow includes liquid supported solids and bubble supported solids. Then liquid supported solids operation characterizes fluidization with liquid velocity beyond the minimum fluidization velocity. So if gas is the continuous phase or the liquid is the continuous phase, depending upon that, the fluidization occurs beyond the minimum fluidization velocity, because about the fluidization already 3 to 4 classes already you have listened, so you know how the fluidization takes place. So a minimum fluidization velocity is there when the liquid is the continuous phase. that minimum fluidization velocity is called the liquid minimum fluidization velocity, and for gas continuous phase it is the gas minimum fluidization velocity. So the different types of flow regimes as we get here, you see in this plot, one is the abscissa, you see the gas velocity, and in the ordinate there is the liquid velocity. So in the low liquid and gas velocity there is the coalesced bubble flow regime, and for the low to moderate gas velocity but high liquid velocity, this region it is the dispersed bubble flow regime we get. And for high gas velocity and low liquid velocity we get slug flow regime. In the slug flow regime, with increase in flow rate, the slug frequency increases, that means flow rate of the gas, the slug frequency increases, and the volume fraction of the liquid decreases. Then liquid solid mixture forms fragmented agglomerates, eventually operate in mode 1B, that means gas becomes continuous and liquid just trickles down in the trickle flow. So another flow regime classification graphically shown here. For all high liquid velocity and a low gas velocity. To the left high liquid velocity, to the right high gas velocity, and to the left the gas velocity is low. So when the gas velocity is low and the liquid velocity is high, dispersed bubble flow you get, smaller bubbles are there in the bed, and these smaller bubbles because of high liquid velocity escape fast at a faster rate from the bed. So overall gas hold up in the bed is little less, whereas if the liquid velocity is high and moderate to high, and gas velocity is little more, then discrete bubble flow we get. Here little larger bubbles we get, little larger bubbles. Here the residence times of the bubbles, because of moderate to high liquid flow rate, the residence time of the bubbles are more, so that the gas hold up in this bed is more. Then the coalesced bubble flow, where the liquid velocity is moderate to less and a little moderate gas flow rate is there, so bubble coalescence takes place. That means gas bubbles which are coming from the distributor section coalesce each other and bigger size bubbles are formed, and a wide size distribution of bubbles are seen in this coalesced bubble flow regime. If we further increase the gas flow rate, then slugs are formed. Slug means large gas bubbles are formed, even up to reaching the diameter of the column, and the length of the bubbles even more than that of the diameter of the column. Such things are there. This is the slug flow regime. Another flow regime is the churn flow regime, where it is similar to that of slug flow, but it is a chaotic behavior of the slugs are there, and a frothy type of the bed we get in the form of froth. The gas and the liquid moves in the upward direction. Next there is a bridging flow regime. Bridging flow regime, you see that liquid forms the bridge. Here it is a bridge, then another bridge is here, in between there is gas is there continuous. So this is a bridging flow. Then further increase in the gas velocity, annular flow we get, that means liquid is just in contact with the wall of the vessel, and the gas phase entirely occupies the central region of the bed, annular flow. Then co-current gas liquid solid fluidized bed. The state of gas liquid solid fluidization is strongly dependent on the geometry of the bed, methods of gas liquid injection, and the presence of the retaining grid. Retaining grid means it is there to check the motion of the solid, that is retaining grid. So depending upon that, the geometry, and you see that tapered fluidized bed is here. So earlier I had shown you in the previous slides, you have seen that cylindrical vessels are there, but here it is tapered conical vessel. Tapered fluidized bed uses a tapered column which diverges at a small angle in the upward direction. And in a spouted bed, the gas and the liquid are introduced into the bed through gas liquid injector. This is gas liquid injector located at the bottom of the bed. The solid particles in the core area are carried out by the fountain and separated from the liquid at the surface of the fountain here. The solid particles then move down in the annular region. So solid moves upward direction like this, then falls like this. Then semi-fluidized bed. A semi-fluidized bed is formed if you arrest the free expansion of the solid particles in the bed by means of a top retaining grid. This is a top retaining grid here. As the liquid and gas velocity is increased through the bed of solid particles, after beyond the minimum fluidization condition, the height of the solids in the bed increases and it may reach at the top of the vessel. And if we put towards the top a retaining grid, so solid particles will form a fixed bed at the top. You see, it is a fixed bed at the top of, or it can be called as a packed bed at the top. So when a mass of fluidized particle is compressed against the porous retaining grid, resulting in the creation of a fluidized bed and a fixed bed in series within a single vessel. At the top you see there is a fixed bed, and below that again the particles are in the form of fluidization. Fluidization means it is the circulation of particles is there. Particles rise to certain extent, then as they lose the momentum fall down again. Because of the drag of the liquid, of flow liquid and gas, again they are lifted to higher position in the bed. So one experimental setup here showing the gas liquid solid fluidized bed. As you see in the transparent vessel, solid particles are there. In the right side figure you see that solid particles are there. Here the figure in the right side shows this the distributor section here, where gas liquid mix up here in this distributor section and enters to the test section, that is the main fluidized bed. This is the test section or main fluidized bed where this fluidization occurs. And at the top you see there is a disengagement section where gas and liquid separates. The gas phase escape to the atmosphere here in this case, but it can be collected also and taken for some other processing. Similarly, the liquid is drained out and taken to the storage vessel from where the liquid is pumped out. Again, it can be taken for other use for a continuous operation. This is a batch 3-phase fluidized bed setup as far as the solid and the liquid is concerned. Liquid is circulating and the operation is continuous for the gas one. So the gas liquid distributor is like this. It consists of one air spurger. It is antenna type air spurger with small holes on this sparger gives smaller bubbles, generate smaller gas bubbles here, or the gas jets which when in contact with the liquid takes the form of bubbles. Then these are the manometers, differential U-tube manometer used for the measurement of the pressure drop, and this is a conductivity probe used to sense the signal of the flow of the gas bubbles. Next, the definition of some three-phase fluidization phenomena. It is classified as a term, symbol, and a significance. The bed pressure drop, usually represented by delta P. It measures the drag in combination with the buoyancy and the phase hold-ups. In three phase, it measures the drag. In two phase, it is only the drag and the buoyancy is of concern. And when it is gas solid fluidized bed in ambient condition, it is the drag is the predominant one, mostly it is drag. But in a liquid solid bed, it is the drag and buoyancy together. But in gas liquid solid system, it is the drag, buoyancy force, and the phase hold up together. Then minimum fluidization velocity, the minimum superficial velocity at which the bed becomes fluidized, that is the minimum fluidization velocity. For the operating conditions, the particles are fluidized primarily by the liquid for a liquid continuous phase. The bed expansion ratio, that means initial static bed height when the particles are not fluidized, which is the fixed bed height. Then with the flow of the gas and liquid, the bed expands, we get a higher height of the fluidized bed. So that height to the initial height, that ratio is known as the bed expansion ratio, measures the extent of fluidization in the bed. So it is the ratio of expanded bed height to the static bed height. Then gas hold up, that means the fraction of the bed occupied by the gas phase, measures the fractional volume occupied by the gas. It is the volume of the gas to the total bed volume. That ratio is the gas hold up. Similarly, liquid hold up is the fractional volume occupied by the liquid, that is volume of the liquid in the bed to the total volume of the bed. Solid hold up measures the fractional volume occupied by the solids. It is the volume of solids by the total bed volume. And the sum of these three phase hold ups, gas, liquid, and the solid, should be equal to 1 because it is the fraction. So the total is 1. Then another one is the porosity. Porosity means the space in the bed which is occupied by the gas and the liquid phases only, which is nothing but 1 minus the volume fraction of the solids in the bed, that is the porosity. Another characteristic is the bubble rise velocity, the actual velocity of bubble as it rises through the bed. And your gas hold up depends upon the bubble rise velocity also. If the bubble rise velocity is very high, residence time of the bubble in the bed will be less and the gas hold up will be less. And for low bubble rise velocity, gas hold up will be more. The qualitative influence of different operating variables. So what are the operating variables? In this gas liquid solid system, the flow rate of the gas, flow rate of the liquid, which is actually represented in terms of superficial velocity of the gas, superficial velocity of the liquid, density of the particles, liquid density, density of the gas phase, surface tension of the liquid, viscosity of the liquid, the particle size, size of the solid particles, the shape factor of the solid particles, phase, and the diameter of the vessel or the column. So few parameters of the bed with which the gas liquid solid hydrodynamics is characterized is nothing but the gas hold up, bed expansion ratio, bed porosity, and the bubble diameter. With increase in the gas velocity, that means higher gas velocity, your gas phase hold up increases, bed expansion also increases, porosity increases, because same amount of solids as it is fluidized to a greater height, the solid concentration decreases and the void fraction increases, that means porosity increases. And with increase in gas velocity, your bubble size increases. With increase in the liquid velocity, the gas hold up slightly decreases, because the liquid takes down the bubbles in the bed little faster than at lower liquid velocity. Bed expansion ratio for increase in liquid velocity increases, porosity increases, and a slight decrease in the bubble size is there. As far as particle density is concerned, there is no clear study how the gas hold up is affected, but bed expansion decreases, porosity decreases. And liquid density, with increase in liquid density, the gas hold up decreases, bed expansion increases, porosity increases, and bubble size decreases. With increase in the density of the gas phase, no such study by varying the gas phase density is there. And as far as the surface tension is concerned, with increase in surface tension, your the gas hold up decreases, and your bubble size increases here. With the increase in the viscosity, this viscosity and the surface tension, okay, they come together because you are varying the liquid, so sometimes they club together. So no clear study is there on the effect of the liquid viscosity on gas hold up, but bed expansion increases, porosity increases. For increase in the particle size, gas hold up increases, bed expansion decreases, porosity decreases, bubble size decreases, and shape factor has no effect, and no such studies are there. And for the diameter of the column, increase in the diameter of the column, remaining other things same, your gas hold up decreases, and the studies, no studies are there for the other parameters. Now we will discuss the hydrodynamics of co-current gas liquid solid fluidized bed. So the main parameters are the pressure drop, minimum fluidization velocity, the phase hold ups, like gas phase hold up, liquid phase hold up, solid phase hold up, your bed expansion, or indirectly it is the directly it is the bed expansion, and the other way indirectly the bed porosity is measured from the bed expansion. So first the pressure drop and minimum fluidization velocity. For a gas liquid solid fluidized system, the minimum liquid fluidization velocity. Liquid fluidization velocity means liquid is the continuous phase, that's why minimum liquid fluidization velocity is the superficial velocity of the liquid at which the bed becomes fluidized for a given superficial gas velocity, because three phases are there, so gas should be there. So at certain gas velocity, what is the liquid minimum liquid velocity required to make the bed of solid particles fluidized? That is the minimum liquid fluidization velocity. Above the minimum liquid fluidization velocity, there is good contact between the gas, liquid, and solid phases are there. And a bed pressure measurements or visual observations are generally used to measure the minimum liquid fluidization velocity, either from the bed pressure drop measurement, like for the liquid solid and gas solid fluidized bed, the previous classes you have learnt, that is done, or it is by visual observation also that is done. So a plot of pressure drop through the bed or the pressure gradient, either pressure drop or pressure gradient. Pressure gradient means pressure drop per unit height of the bed. Within the bed versus the superficial liquid velocity displays two linear regions whose intersection corresponds to the minimum liquid fluidization velocity. You can use the visual observation. You can see that as you are increasing the liquid velocity through the bed, initially the bed is stationary, a fixed bed is there. Now the particles will start to move in the upward direction. Okay, that corresponding velocity is the liquid minimum fluidization velocity. That is visual observation, but from the pressure drop measurement also we can have that. So how the pressure drop varies? At zero velocity the pressure drop is zero. As you increase the liquid velocity, the pressure drop will increase because the liquid will impart drag on the solid particles, and the pressure drop is nothing but the representation of the drag force of that the fluid exerts on the solid particles in the bed. So here you see the liquid pressure drop with liquid velocity increases like this. This is one experimental plot, and experimental the velocities are varied in such a way that exact point we are getting here at the minimum fluidization velocity. After that the bed pressure drop remains constant, almost remain constant, or in a gas liquid solid fluidized bed little increase in the this will be there, that bed pressure drop increase will be there, it will not be constant because of the volume fraction of the phases. As the volume fraction of the phases will change, that means phase hold up will change. For that there will be some change in the overall bed pressure drop value, which is not there in the liquid solid bed or gas solid bed, because additional term here is the drag is there, buoyancy is there, and a phase hold up is there, as I have already told. And this is one ideal situation where the beyond the minimum liquid fluidization velocity the bed pressure drop remains constant. But your experimental observations may be like this. If you are carrying the varying the superficial velocity and bed pressure drop data, here is 1 point like these points are there, and you do not have experiment exactly at the minimum fluidization velocity, but you have the pressure drop values for liquid velocity is higher than the minimum fluidization velocity. So a linear line like this is there, and another horizontal line. The intersection of that here, this is considered as the minimum fluidization velocity. And the bed pressure drop or the bed pressure gradient or pressure gradient in the bed is given by this expression. G is the gravity times of density of the gas phase multiplied by the volume fraction of the gas phase plus density of the liquid phase multiplied by the volume fraction of the liquid phase in the bed plus density of the solid multiplied by the volume fraction of the solid phase in the bed. So that constitutes the pressure gradient in the bed. The variables on which the liquid minimum fluidization velocity of a gas liquid solid fluidized bed depends are gas velocity, this is one operating variable, particle size, particle density, liquid viscosity, liquid density, static bed height, shape of particle, and the gas liquid distributor. Because it is the liquid minimum fluidization velocity is mentioned, that's why the liquid velocity is not written here, whereas the liquid velocity is also a variable. Basically liquid velocity is also a variable, but it is liquid minimum fluidization velocity, so its dependence is written, that's why the other factors are there, because liquid is the continuous phase. So it's a minimum fluidization velocity we are going to determine. The following figures which are there in the next slides describe the behavior of a liquid minimum fluidization velocity to some of these variables. As you see here, the effect of gas velocity. These lines are for different gas velocities. Gas velocity remain constant. One is 0 gas velocity, that means only the liquid solid fluid bed here. The pressure drop variation is represented by this. And as you increase the gas velocity, your total pressure drop what you measure decreases. For the same amount of solids in the bed, okay, the pressure drop is nothing but the representation of the drag, buoyancy and the phase hold up together. So for liquid solid bed, it was the drag force, it was such high, and as you increase the gas velocity, the overall bed pressure drop as you measure that decreases, and finally for 1 meter per second of the gas velocity, okay, the variation of pressure drop with liquid velocity is like this. As you increase the liquid velocity at a constant gas velocity, your pressure drop increases, whether it is liquid solid fluidized bed or it is gas liquid solid fluidized bed. Then at the minimum fluidization velocity, beyond the minimum fluidization velocity, the pressure drop becomes constant, almost constant. So as you see here, for liquid solid fluidized bed, this is the minimum fluidization velocity. For gas liquid solid fluidized bed, for gas velocity of 0.2, this is the minimum fluidization velocity, whereas for the gas velocity of 10 meter per second, this is the minimum fluidization velocity. So as you see, the minimum liquid fluidization velocity decreases with the gas velocity. Higher is the gas velocity, that means gas also contributes for the fluidization of the solid particles, that is suspension of the solid particles. So the amount of liquid that is required to support the solid particles gradually becomes less, so that liquid minimum fluidization velocity decreases. And effect of particle size, higher is the particle, higher is the liquid minimum fluidization velocity. You see that 3 different particle sizes are there: 2.18 millimeter, 3.05 millimeter and 4.05 millimeter. So for 2 point, you see this is the minimum fluidization velocity. For the 3 millimeter one, this is, and for 4 millimeter, okay, this is the minimum fluidization velocity. That means minimum fluidization velocity increases with the particle size. That means the particles are of higher weight, so need higher drag force to get fluidized. And the particle density, lighter particle, coal particle is this, whereas the dolomite is this, having higher particle density. With the particle density, obviously the weight of the particle increases. For the same size of the particle, weight of the particle increases. As the weight of the particle increases, you need higher velocity of the fluid to offer the amount of drag that is necessary to make the particles suspended in the bed. So with particle density, increase in particle density, bed pressure drop increases. Then effect of liquid viscosity. Liquid viscosity, viscous liquid at low velocity also the drag is more, because it is viscous. Viscosity is more, so drag is more. So that if the liquid viscosity is increased, here in this you see that one is water, 6% glycerol, and the glycerol percentage is varied up to 24%. Highest viscosity is for the 24% glycerol. For water system, you see this is the minimum fluidization velocity here. So it is a exact plot. As you see, beyond the minimum fluidization velocity, slight increase in the bed pressure drop is there. But you see that slope of the curve is different. Up to this is one slope. Beyond that, there is another slope of the line. This is for the increase in the liquid velocity. X-axis you see superficial liquid velocity is there. As you increase the liquid velocity, the bed pressure drop variation is like this. So why it is like this, that we will discuss later. Now you see that with increase in the glycerol percentage, that means a higher viscosity of the fluid, the minimum fluidization velocity decreases. That means less velocity is required to make the bed fluidized. Then effect of initial static bed height. If you just change for the same particle system, okay, different amount of particle if you take, that means bed mass you vary. There is no effect on the minimum fluidization velocity. Minimum fluidization velocity is nothing but the liquid velocity that is needed to make the solid particles suspended. Unless there is variation in solid density or particle size, simply increase in the bed height does not change the liquid minimum fluidization velocity, whereas what is changed, you see that drastic difference in the overall bed pressure drop is there. For a bed height of 17.7 centimeter, you have the pressure drop, fluidized bed pressure drop, this value, whereas for 26.7 centimeter, you have a fluidized bed pressure drop this, and at 36.7 centimeter, you have this value. Because more amount of solid, so more mass, so higher overall pressure drop is required. But the liquid velocity that is offering drag to a single particle to make it suspended is not changing. So right side this plot shows the variation of a minimum liquid fluidization velocity with gas velocity. So as you see that with increase in gas velocity, the minimum liquid fluidization velocity decreases. Then already about the gas solid fluidized bed and liquid fluidized beds, you know that the experimental observations are correlated to some mathematical equation which are known as the correlations. So correlations are developed for different types of operation in the different types of processes, and the correlation for the minimum fluidization velocity are like this. So the liquid minimum fluidization velocity, as we have discussed, it depends upon the gas velocity, particle size, liquid phase viscosity, density of the solid particles, density of the liquid, and your shape factor. So one thing is missing here, which was there, the gas phase density. So for the gas, unless it is a compressed gas, the density of the gas does not change much. As far as the solid to gas, that density difference is there. A solid may be having a density of 1000 minimum kg per cubic meter, whereas the gas air at atmospheric condition, it is having the pressure of 1.2 kg per cubic meter. So any variation little bit, if you take a if you take air or if you take carbon dioxide. Carbon dioxide is a little heavier gas, but still it won't be more than 1.4 kg per cubic meter. So large difference is not there. Because of that, the gas phase density is not contributing to this, and the correlation is developed. Using this correlation, if you have different gas velocity, particle size, liquid viscosity, and gas your solid phase density, liquid density, and the shape factor you have, you can determine the liquid minimum fluidization velocity required to make the particles fluidized. The first equation is in the dimensional form, another equation is in the dimensionless form. Dimensional means it is the liquid minimum fluidization velocity, either it is meter per second, centimeter per second, having the dimension and the unit, whereas it the ratio of a liquid minimum fluidization velocity to the liquid minimum fluidization velocity in the liquid solid system only. No gas is there. In that ratio, it is dimensionless form. Again another expression is there for that. Then this it can be combined to different types of other dimensionless factors. Instead of the gas velocity, particle size, liquid viscosity and densities of the phases, it can be combined into dimensionless groups. Here this third correlation you see, that is in terms of Moton number, then Archimedes number and gas phase Froude number. This is Froude number, you know. This is Archimedes number and this is a Moton number. So this way the correlations are there. For the scale of the system, this type of dimensionless correlations are good. But for the calculation of the liquid minimum fluidization or any other parameter, such correlations are easier to have the calculation on that. Next hydrodynamic parameter is the solid hold up and bed porosity. So as bed porosity we have discussed. In the left hand side one photograph is here. You see that it is a almost a fixed bed. It is little bit fluidization is there, almost a fixed bed. So as you increase the liquid and gas velocity, your bed get fluidized, solid particles are suspended. Now height of the bed is this. So height of the bed increased. So this is nothing but known as the expanded bed height. This is the expanded bed height, HE we can write, and this is HS, static bed height. So the ratio of HE to HS is nothing but the bed expansion ratio. As the bed expanded, so the void space between the, because in the packing we call as the void space, it is not the void space but the free space in between the solids, that you consider as the bed porosity. So bed porosity increases with the expansion of the bed porosity increases. So bed porosity is a parameter which is used for the calculation of many things. That's why it is in the form of bed porosity, but usually for any experimental observation or anything for the sizing of the system, it is not the bed porosity, rather the expanded bed height is of importance. So what should be the height of a fluidized bed? Depending upon the porosity you need, your expanded bed height will be there. And once you have the expanded bed height, the highest expanded possible bed height is there. From that you will design your system, that height of the fluidized bed you will design. Otherwise what will happen? Particles will come out from the vessel. Suppose it is the vessel top, now it is fluidized up to this. If I further increase the liquid velocity here, then what will happen? The particle will further expand and the particles will come out from the bed. So sizing of the system, the height is one parameter, diameter is another parameter. The solid hold up in the bed is expressed by this. This is the mass of the solids upon the density of the solid. This is the column area of the column, cross sectional area of the column, and it is the expanded bed height. So cross sectional area of the column multiplied by the expanded bed height, that is the total void volume. Mass of solid to density of the solid, this is nothing but the volume of the solid. So which is nothing but the volume of the solid to the volume of the bed, it is basically. That is nothing but the solid fraction, solid hold. And bed porosity is nothing but 1 minus the solid hold up, which is the sum of the gas hold up and the liquid hold up. From the knowledge of solid mass and the expanded bed height, the bed porosity can be calculated. So usually any experimental finding is represented in terms of expanded bed height or bed expansion ratio, which is again converted to bed porosity. The expanded bed height is generally observed visually if particles are little large in size. That means visually you can see the particles inside the bed, and if the vessel is a transparent one, or from pressure gradient measurement. along the length of the column or by sensing the signal from conducting probe or optical probe. So any conducting or optical probe, if I keep in the bed, suppose this position one probe is, this position one probe is, this is this position another probe is there. If solid will reach this signal from this probe I will get a different signal. If the solid particle will reach here, then this probe will give the signal. Similarly, the other probes they will give the signal. Using that we can have, or otherwise the pressure gradient. Pressure gradient means the total pressure drop upon the height of the bed. So if you have the pressure ports at different locations you may have the pressure port. Using those pressure port, if you measure the pressure drop, also the expanded bed height can be known. Like if the solid particles below this probe, okay, your pressure gradient will be something. For gas liquid phase only, above that, okay, one pressure drop will be there. And once the solid particles will reach this here, this point, and it will be above that. So the amount of solid particles they are just above this port will give a different pressure drop value. So pressure gradient along the bed will be different. From that also the expanded bed height can be measured in a opaque system. The following are some typical bed expansion behavior of a three-phase fluidized bed experimentally observed. You see in this plot, this is a bed expansion ratio in the ordinate, and in the x-axis there is superficial liquid velocity, and the legend shows that different gas velocities are there. So these lines represent different gas velocities and the variation of bed expansion ratio with liquid velocity. As you see, with the increase in the gas velocity, the bed expansion increases. For the same liquid velocity, you see, this is the liquid velocity. So at 0.08 meter per second of the liquid velocity, for a liquid solid bed without the absence of gas, this is the height of the bed, you can say, or it is the bed expansion ratio. But as you increase the liquid velocity, increase the gas velocity is increasing, so you see the bed expansion ratio is more. That means height of the expanded bed is more. So bed expansion ratio increases with the liquid velocity and with the gas velocity. Next is the plot of the bed expansion ratio with the particle size. Higher is the particle size, less is the bed expansion ratio. Here you see larger size particle, this is the bed expansion ratio variation with the liquid velocity. Smaller is the particle, to a more height it is getting fluidized. Expanded bed height is more and bed expansion is more. Particle density has a significant role on the bed expansion ratio. With increase in particle density, the bed expansion ratio is less. For coal, the bed expansion ratio is the highest, then followed by this dolomite having dense specific gravity in the range of 2.6 to 2.8. Coal is having 1.5 to 1.6. Iron, this is iron ore. Hematite, it is in the range of 3.8 to 4.2, whereas this is laterite, it is close to 5 specific gravity. So as with this, your bed expansion with increase in the particle density decreases. Then liquid phase viscosity, more is the viscosity of the liquid. More should be the expansion. 6% glycerol, you see this 6% glycerol is this, whereas 24% glycerol is this. So more is the viscosity, more is the bed expansion. Little bit bed expansion is more. But this is one experimental finding which was earlier that was not available, because the qualitative influence of different variables as I had discussed in the table, this thing was missing. Bed expansion ratio, effect of initial static bed height. Initial static bed height has no effect on the bed expansion ratio because it is the expanded bed height to static bed height ratio we are measuring. But more is the amount of solids, to a more height it will go, but the ratio is almost constant if you see. So then the bed voidage is calculated from this bed expansion ratio, and this plot shows the bed voidage calculated here from different types of correlation. It is calculated, and experimentally also it is calculated at different gas velocities and liquid velocities, and at different gas and liquid velocities the variation of the bed voidage is represented by this, because the bed expansion ratio varies with gas and liquid velocity, which already you have seen. Accordingly, the bed voidage also varies. The bed porosity has been found to be a strong function of the liquid velocity and gas velocity, particle density and particle size, but comparatively a weak function of the liquid viscosity, static bed height and a size of the column. So few things are shown here with the, you see that liquid density, not much effect there, liquid viscosity also not much effect is there. Again, correlations are developed for bed porosity in dimensional form, different dimensional form. This is the different correlations for the bed voidage. This bed voidage epsilon is nothing but the sum of the volume fraction of the gas and a volume fraction of the liquid in the bed, and this is the void fraction or the bed porosity for the liquid solid bed only, no gas is there. For that the relation is like this, whereas because the gas velocity term is missing here, as you see in this relation, but other correlations, that is the gas velocity term is there. One is this is the bed porosity, this is the bed expansion ratio. Similarly, for the liquid solid system, the bed expansion ratio is this. And in dimensionless form, whether it is the bed porosity or the bed expansion ratio, in the form of a ratio of these to that of the liquid solid system is represented. So the bed expansion ratio of the gas liquid solid fluidized bed to the liquid solid fluidized bed is expressed by this correlation, whereas the bed voidage for the gas liquid solid system to the liquid solid one is given by this relation. So these correlations can be used for the calculation of the bed porosity if you know the situation of the operating conditions. Then the other hydrodynamics parameters are the bed pressure drop and a phase hold up. Equations used to determine the volume fraction of each phase in a three-phase fluidized bed are: one is the sum of the volume fraction of gas, liquid and solid phases equal to 1. Then the pressure gradient relation, this is delta P upon delta H, which is G times of rho G epsilon G plus rho L epsilon L plus rho S epsilon S. And the solid fraction, solid can be measured easily, amount of solid in the bed, and if you have information of the amount of the solid in the bed, that is the mass of the solid, then you can determine the solid fraction. Other promising methods for measuring the local gas hold-up are electroresistivity and electroconductivity methods, that is gamma ray transmission measurement and radioactive tracer techniques. Some of the techniques are invasive in nature, and some of the techniques are non-invasive. So what is invasive? If you are inserting a conductivity probe, then it is disturbing the situation of the things in the bed, and if you are not inserting any foreign substance, using gamma ray radioactive tracer, we can scan the bed, so that it is a non-invasive technique it will be. So here in one experimental setup, this is a conductive probe is shown. The either it is a single probe or it is a dual probe. Dual probe means one suppose bubble is moving, it is touching this probe, it will have one signal. Another it is touching this, then it will have another signal. Then through this the bubble rise velocity can be measured. Suppose the first signal at some time for this probe we get, then for the same bubble another signal we will get from this from the other probe, so that how much time difference is there, from that the bubble rise velocity can be determined. Also the size of the bubble can be determined. If it is touching this probe and this probe together, we will have a one kind of signal. If it is touching only one probe, not touching the other probe, that means the bubble size is smaller than the distance between the two probes, so size cannot be measured. But for a single probe, only when the gas is touching the probe, you will get a different signal, and the signal transmission using this type of arrangement can be done. So as you see, the signal is captured here. When in the absence of the gas bubbles, this is the line that is representing, that is for the liquid in the system. This is the signal, and when the gas bubble is touching that, depending upon the size of the gas bubble, you have a signal like this, down signal you are getting. And these are the different points, such a way if you take the signal and average it over the entire bed, then average bed, gas hold up in the bed you will be able to determine. Another more direct method is a phase isolation method, in which we simply isolate a representative portion of the test session by simultaneously shutting down two quick closing valves. Through in the liquid line and the gas line, if we install quick closing valves, suddenly that can be closed, so that the flow of the liquid and the gas to the bed will stop completely. As it will stop, the gas will escape the bed, only liquid and solid will be there. That means the bed height, the overall that two phases, liquid and solid bed height, or it is the liquid height in the bed will be something. So from that this can be measured. So say suppose it is the height of the expanded bed. Now with the escape of the gas, this is H, and with the escape of the gas, only the liquid solid, the height is this is HL. This can be easily measured, and the hold up can be calculated from that using this relation, H minus HL upon H times of 100. This is nothing but the gas hold up in percentage, but fractional gas hold up no 100 is required. So gas hold up variation with gas velocity, liquid velocity is like this. So the effect of this is for different gas velocities. Variation of liquid velocity is there. So with the liquid velocity at different gas velocities, the gas hold up decreases slightly. It is not a strong function of the liquid velocity, whereas here with the variation of the gas velocity, the gas hold up increases significantly. But with liquid velocity, at different liquid velocities, these values. So for this gas velocity, if the liquid velocity is different, no drastic change in the gas hold up is there. So for different viscosity of the liquid and the liquid density, it is basically not the density of the liquid, rather the liquid viscosity. So liquid viscosity is there, and with these different liquids, your surface tension is also different. So combined effect is there on the gas hold up. As you see, for the water system, this is the gas hold up variation with the liquid superficial velocity, whereas for 24% glycerol solution, this is the value. That means gas hold up is more for higher viscous solution than that of the low viscosity liquid. The gas hold of variation with liquid velocity to gas velocity ratio. Liquid velocity to gas velocity ratio, you can see that two different regimes are there. One regime is this up to one kind of slope, another is this kind of slope. So if liquid velocity predominates, you have the gas hold of values, less gas hold of values, and when gas velocity predominates, you have higher gas velocity, gas hold of values. Similarly, your liquid velocity, your with increase in the liquid velocity, your liquid phase hold up increases because more liquid is there in the bed, that is as per the inventory. So liquid hold up increases, and with gas velocity, liquid hold up decreases slightly. So correlations are developed for gas hold up. The gas hold up correlation in dimensionless form and dimensional form are available here. In dimensionless form, it is the Mohan number, Etovas number, liquid phase Froude number. This is the ratio of diameter of the particle to the diameter of the bed. This ratio, these are in HR means height ratio, then gas phase Froude number and the particle shape. So many factors are correlated. They have the gas hold up value depends upon these variables which are combined to dimensionless units. Okay, let me finish this class here. Another computational hydrodynamic study of this gas liquid solid fluidized bed, little bit I will discuss in the next class. Thank you all. Any questions? Participant, if any question is there. If no questions, then thank you. I stop here.
whether it is just 1 minute. Coming sound? No, it is. Hello? Sound is coming?
Yes, ma'am. Coming.
Okay, for first order solid catalyzed gas phase reactions, we can express the reactions that is in various ways. Suppose we can calculate the rate for unit volume of the catalyst volume if you take Vs, and then we can write that minus 1 by Vs dNA by dt Kr Ca, where Kr is the reaction rate constant, and if you consider the Vs, that is the catalyst volume constant. So, here from this we can measure the rate constant, which is independent of the bed voidage and particle size also. Now, if we because here we are considering the catalytic reactor, here we are not considering the diffusion mechanisms. So, here if diffusion effects we do not consider or do not introduce. So, here it is we can connect or we can link the reactor performance to the fixed bed, performance of the fixed bed to the fluidized beds. Now, slide is not changing. 1 minute. Just 1 minute. Slide is not. Escape doing. Okay, let me share once again. It is. Yes. So, if you write that that is feed rate is the V meter cube per second of the reactant gas having the concentration inlet concentration CAI to catalyst bed, where the solid volume catalyst volume is the Vs, and now you can integrate the performance expression and if outlet concentration is CaO, we can write for the plug flow reactor 1 minus Xa equal to CaO by Cai, which will be exponential minus Kr tau. Now, for mixed flow reactors 1 minus Xa CaO by Cai equal to minus 1 by 1 plus Kr tau. Now, here where the reactor ability that is to measure is the tau, which will be volume of the catalyst or the solid particles divided by volumetric flow rate of the gas. So, Vs by V. Now, the dimensionless reaction rate will be Kr into tau. So, which will be Kr, which this equation we will be using in the numericals, that is the volume the dimensionless reaction rate Li into 1 minus epsilon I divided by U0. So, here volume of the catalyst means how much, if you take the length of the bed Lf, now it will be 1 minus epsilon f and divided by volumetric flow rate of the gas. So, then we can get this dimensionless reaction rate. As I told, depending on the particle size, the catalytic reactors we divide in the 4 groups also. Now, first is the if Geldart A particles we are considering, where the models for the vigorously bubbling fast bubble means a small bubbles will be forming, fine particles Geldart A not cohesive, fine particles are taking. So, here thin cloud will be forming. As I told that is, so in the fluidized bed we can say that it is consist of the emulsion phase and the solid phase. suppose the or the bed that is when the it is uniformly fluidized all along the bed, solid materials is there, we can say that almost it is the emulsion phase only, means solids in the fluid state it is there entirely. So, it is the emulsion. Now, in this figure we can say it is the bubble phase and it is the emulsion phase, and it is surrounded by the thin clouds. You can see this thin cloud is formed by the gaseous reactant. When the gaseous reactant pass through the bed, that is you can see here CAI. Now, initially small bubbles will be forming because here pores are there in the distributor. When the gas is flowing through this, small bubbles will be forming, and these bubbles coalesce with each other, tend to form the larger particles. But what happens here, as it is the bubbling bed for vigorously bubbling, as continuously bubbles will be forming, that will be moving. Now, here as the bubble movement or bubble speed is faster than the gas velocity, here you can see bubble for this is the condition that the bubble velocity with which bubble is rising is greater than the minimum fluidization velocity. So, here the this gaseous reactant form the cloud here, means surround the bubble, a thin layer is formed surrounding the bubble. Then when the bubble will be moving, that cloud also slowly moving, and here in this below this bubble, this will be the wake region. That is morning sir was saying also, whether it is the liquid 3 phase or the 2 phase. So, in this region will be the wake region, in where the some solid particles, because some pressure difference is created when the bubble moves through that wake region, the some solid particles are dragged into this wake region. When the bubble moves, those solids also move with that. Now, here bubble moves faster and than the superficial velocity. So, by which what happens, when the bubble will be moving faster, so thin clouds will be again on the top, it will be broken, and then it will be moving again, another cloud will be forming because it is continuously fluidized. So, on the upper region also some gas or gaseous reactant already there. So, here you can see that in the cloud region, this is the cloud region, this is the emulsion that is in the bed, it is the solid particles is getting fluidized throughout the bed, it is there emulsion region, and this is the bubble is there. So, here thus if you consider any section wise for any height, you can see here the how the movement is bubble is moving at this bubble velocity, and here the cloud to emulsion, you can see cloud to emulsion, the gaseous movement is there, means it is reversible, emulsion to cloud, cloud to emulsion, and here you can see bubble to cloud, from the movement gaseous reactant movement will be there, bubble to cloud, cloud to bubble, and then cloud to emulsion, emulsion to cloud. Again here you can see some gaseous reactant here from the bubble to entering the cloud, constantly it is entering the that is emulsion phase also. So, with this mechanism reaction takes place. So, here basic principle is that overall disappearance in bubble will be reaction in the bubble plus transfer to cloud wake. As I told, when the gas is entering the bubble is moving at a faster speed. So, naturally the disappearance in the bubble, overall disappearance, the gas will be when the bubble will be moving, the gas will be forming again the cloud for the successive bubbles which will be coming out from the lower region. So, thus there will be some within the bubble also some solid particles are there. So, reaction in the bubble plus, because reaction of the gaseous reactant with the solid particles which are already present in the bubble and transfer to the cloud wake region also. Some solid particles are the gas are there in the cloud region. The gas also, when the bubble moves out, some gaseous reactant also flows to the comes to the wake region, that is in the cloud, lower part of the cloud is the wake region. So, there in the wake region also some gases transferred. So, transferred from the cloud to wake region, we can break again into two components, that is reaction in the cloud wake region, because cloud wake region also particles are there. So, with that also the reaction is taking place, again transport to emulsion. So, some gaseous reactant is getting transport to emulsion. So, that is why in that figure we saw it is reversible, cloud to emulsion, emulsion to cloud. Then transport to emulsion, it is the in the emulsion phase, it is transferred to when gaseous reactant is there either from the bubble or from the lower region. When the gaseous reactant is moving to the directly to the emulsion, there will be reaction in the emulsion also. So, this is the first type of the reactor, how the as bubble moves faster than the gaseous reactant, reaction is taking place all cases, that all places, that is in the emulsion, in the bubble, as well as in the cloud wake region. So, second type of the reactor will be for a bubbling bed of the intermediate size particles. Intermediate size particles means it will be AB category, means slightly means larger than the B, but clearly not the B, it is AB, intermediate size particles is there, where we can say that UMF by epsilon MF, that means you can say that fluidization velocity UF will be UMF by epsilon MF is less than the bubble velocity, but it is less than 5 times the fluidization velocity, means it is more than the bubble velocity is more than the fluidization velocity UF, but it is less than the 5 times the fluidization velocity. Here you can see for intermediate size the bubble movement slows down, the here you can see bubbles is there, the gas is moving faster. So, here bubble to cloud, and that is why what happens, instead of forming the cloud, here immediately gas considers this gaseous reactant which comes from the bottom, it uses this as a bubble, as a shortcut, a path, shortcut path, enters it and leaves at the top, because gaseous reactant is moving faster than the bubble. So, it leaves the top of the bottle and top of the bubble and moves faster, and finally that is leaves the fluidized bed. So, thus here when it is leave the bubble, because entering from the bottom of the bubble, as gas moves faster, gas speed is more. So, here what happens, it comes out, it using the bubble as a shortcut path and comes out of the bubble, then in the emulsion the reaction will be taking place. You can see the gas is entering and coming out. Here you can see where in the emulsion, that is the fluidization velocity will be UMF by epsilon MF, and this is the UB, and here the means almost cloud will be broken, it is so you can see that in the what is the mechanism. So, there in the we saw that cloud formation was there. So, first order irreversible catalytic reactions, an accounting of the reactant gas A as it passes through the two sides, two side by side regions, it gives disappearance in bubble, that is reaction in the bubble, transport to the emulsion, and this transport to emulsion will be reaction in the emulsion and transport to bubble. So, cloud part is not there, as because it is moving, gas is moving faster than the bubble. Third type of the reactor, where it is bubbling bed of the large size particles. So, here further the bubble movement also slows down, because when the particle size is small or the fine, the bubble moves faster than the gaseous reactant, but when the size increases, the bubble speed gradually decreases, or we can say that gaseous reactant moves faster. So, here you can see also it follows the path this PQ, means it is entering, and here also it is leaving, means it is successively entering the bubbles and the leaving at the top, and here in the bed is almost you can say divided into the two phases only, means there in the intermediate size particles some thin cloud might be formed, but here cloud will not formed at all. So, here you can say that is rise velocity of the gas in the bubbles UV star, it is saying will be bubble velocity plus 3 times the UMF. Here UV bubble velocity is less than the fluidization velocity, it follows the path P to Q, which shows the behavior of a typical element of the gas, that is at any level of the bed the distribution flows between the gaseous reactant and bubble will be U0A will be, that is fluidization, that is superficial velocity into the area of the reactor. Or the bed area you can say flow through the emulsion plus flow through the bubble. How much gas is entering, that much is passing to the emulsion and and also flowing through the bubble. Means at any time if you see the gaseous reactant, either it will be summation of the particular element if you are considering in the emulsion phase and in the bubble phase. So, which is 1 minus delta into UMF into A plus delta UB plus 3 UMF into A, where from where here we can say that is the bubble delta is the bubble fraction, which is U0 minus UMF by UB plus 2 UMF. So, bubble fraction, that is how much bubble fraction means how much portion of the gas is remaining in the bubble, that we can say. So, here the fraction of the gas that passes through the emulsion and contact the solids, when it is passing through the emulsion, where in the emulsion it is the gases, the solid particles are there. So, the gaseous reactant is in contact with the solid particles constantly, it is in the contact with that. So, that fraction of the gases which passing through the emulsion phase, and that is the delta will be passing through the bubble phase, and here it is the fraction passing through the emulsion phase, which we can calculate as 1 minus delta UMF by 1 minus delta UMF plus delta UB plus 3 UMF, where UB is the bubble velocity, UMF minimum fluidization velocity. So, which will be solving this UMF by U0 1 minus delta. Now, if you ignore the conversion in the bubble phase, means there is no conversion, because very little amount of solid will be there in the within the bubble solid particles. So, we can ignore that those solid particles are not reacting or the not getting converted. So, this equation which represents the fraction of the bed solids contacted by gaseous reactant as it passes through the bed, then only you can say that it is the fraction of the gas in contact with the solid particles. So, comparing this equation with the plug flow expression, which we discussed fast plug flow and mixed flow reactor expressions. So, then we can write this performance expression in this regime of the reactor. 1 minus XA will be here plug flow we had written, that is it is the rate reaction rate 1 minus means how much fraction is getting converted, 1 minus XA CaO by CaI which is exponential minus Kr tau into fraction of the gases which is in contact with the solid. So, thus here 1 minus XA. So, substituting this fraction here we can write it is 1 minus XA is exponential minus Kr, and in place of the tau, as it is the volume by volume of the solid particles divided by superficial velocity LF 1 minus epsilon F by U0 into this UMF by U0 into 1 minus delta. Here 1 minus delta is there. So, thus we can get now comparing to the plug flow reactor efficiency. Here the efficiency also we can calculate for this reactor model 3, it is the for the large size particles UMF by U0 into 1 minus delta. You can get the efficiency also. as the under the minimum fluidization condition, the bed voidage epsilon mf is about 50% of the bed volume, that is 0.5. So, and also we know that this UMF by epsilon mf is greater than the bubble velocity, this type of the reactor, where we can determine that how delta cannot exceed reasonably 0.25 to 0.35, because if we are exceeding this epsilon mf will be exceeding the 0.5 also, but epsilon mf cannot. With this we can substitute in the expression for the delta, we can check that, because delta cannot exceed 0.25 to 0.35 in this contacting regime, and only when u0 is 2 to 2.5 UMF. So, if you take u0 2 to 2.5 UMF, we can check this delta. U0 is, if you are taking 2 to 2.5 times UMF, if you are substituting here 2 times U0 as 2 times UMF. So, it in the numerator only one UMF will be there, and here UB also, as it is U0 2 to 2.5 velocity times. So, here epsilon mf we can calculate delta, here it is not should not cannot exceed with these conditions. Here substituting again UB bubble velocity, here it will be U0, if we bubble velocity also we take nearly the 2 types the UMF, it will be 4 UMF. So, here it will be UMF by 4 types UMF. So, thus it will be 1 by 4, that is 0.25. So, here we can see that this is the delta should not exceed, if it is we are exceeding U0. So, then it will exceed these conditions. So, for which what happens, the here epsilon mf will also be exceeding that. So, but it is nearly equal to 0.5. So, we cannot exceed more than that. At higher superficial velocities, if we take the higher velocities, that is more than this 2.5 UMF, then there will be channeling, slugging or explosive bubbling will be there, which will replace the ordinary bubbling behavior. That means, here the channeling means this the bubble phase whatever is there, it will be more, means the layer wise solid particles will be there, the entire column will be the entire cross section of the column will be filled with the bubble. So, as a result the top layer one solid top solid layer will be there, middle another layer, and that way different layers will be there which are not in contact with each other. As a result, uniform mixing or the uniform heat transfer, mass transfer will not occur. So, that is the slugging. Or channeling means all the bubbles will be forming in a will be there in a line, in a vertical line, that a channel will form, that also will affect the fluidization phenomena. So, if you are taking the this velocity, superficial velocity more than the 2.5 times the minimum fluidization velocity, then channeling, slugging may occur, or more bubbles will be forming, explosive bubbling will be there. So, ordinary bubbling behavior will be affected. So, one example will be solving. Before that, just last type of the reactor which will be where also gaseous reactant gets converted, that is the reactor model for the free bode region, that is above the bed, as yesterday also I was telling the free bode. So, here the when the solid particles are there in the this the solid initially when fluidization takes place, some before the takes place whatever the material is taken, that is the bed volume is there, and when the fluidization takes place some of the particles will be forming or moving up to certain level, but beyond that, that is the region that will be the splash zone, that is it will be expanded, and just within that it will be fluidizing, and beyond that what happens, it is the very fine particles or the lighter particles will be moving up, and that is the freeboard region, and some solid particles may go there also, but immediately they fall down because its gravitational force, that is the terminal velocity, may exceed the superficial velocity, because of which these particles may fall down. So, here this in what happens, as the gas solid contact increases, here the it is researchers found that here the some gaseous reactant is moving, along with that some fine particles or the some coarse particles also moving. In this region also, where very small quantity of the particles will be there also reaction will be taking place. So, that is the freeboard region, reaction takes place. So, above the fluidized bed, and here and researchers show that contact efficiency between the catalyst and the reactant gas increases. This as contact, they also remain in contact in the freeboard region. There also the reaction takes place in the freeboard region. On this basis, the Cooney-Levenspiel, the researchers, they presented a reactor model, that is this fourth model, for estimating this added conversion in the freeboard region. In addition to the main bed region, whatever reaction is going on, again some reaction also is going on in the freeboard region. So, although the freeboard region, the concentration of the solid is very less, it is that can be extended to the relatively dilute contacting of the fast fluidized beds. So, thus here also the that is letting the density of the particle, if you are taking at any level ZF in the splash and the freeboard region, the then mean density if you rho bar. So, here we can write the mean density will be rho 0, that is whatever initially we have taken, rho 0 into exponential minus A into ZF at any height ZF. So, this is the fourth type of the you can see here the efficiency as versus the bed height it is taken. So, thus here the mean density is to be considered, because in the bed region density will be higher, and here in the freeboard region density will be less also. So, mean density is to be calculated, based on that efficiency can be calculated. Now, one numerical will be just because 4 types, 4 reaction examples are there, but just one I just considered one, because it will not take not be possible to solve all the 4 reactor examples. So, this is the, suppose Geldart B particles are fluidized at the fluidization velocity of the 0.25 meter per second in a baffled bed, where the bubbles are kept small and bubble diameter is 0.025 meter. So, thus conversion factor we have to calculate the conversion factor for reaction rate constant is the 1.5 meter cube per gas per meter cube catalyst per second. So, here data given. So, for gas diffusivity is given 9 into 10 to the power minus 5 meter square per second, and particle density is 325 micron meter. Now, the mean voidage is 0.42, which is you can say that in the fluidized condition also, that is epsilon m f same, that is Lm length of the fluidized bed 0.8 meter, and minimum conditions the fluidization voidage is 0.45 and minimum fluidization velocity is 0.21 meter per second, and gamma b that is 0. So, here for this we need to calculate the conversion, how much gaseous reactant is getting converted. So, here let me share the whiteboard, with that we will be doing. Yes. So, here yesterday I was saying that some bubble velocity UV, how we can calculate, and sorry, bubble rise velocity. So, here UBR, U subscript UBR, it is just I was telling, but not 0.711, 1 minute, 0.711 into G dB to the power half. It is the bubble rise velocity. Now, the bubble velocity will be UB U0 minus UMF plus UBR. How it is coming? See, U0 means how much at what velocity the gas is coming, superficial velocity from the bottom. UMF under at what velocity it is getting fluidized, the solid particles are fluidized. That means excess velocity whatever is there, that will applying some extra pressure on the bubbles to move up, plus the bubble rise velocity if you write. So, then we can get the bubble velocity, that is the excess velocity above the minimum fluidization plus the bubble rise velocity. So, that will be the bubble velocity with which it is moving. So, here the substituting this as bubble diameter is given. So, UBR we can calculate. So, UBR will be 0.711 into G 9.81 into bubble diameter 0.025 to the power half. So, UBR is coming, calculating, it is coming 0.3521 meter per second. So, bubble velocity is, we can write here one line you can give. Now, U0 superficial velocity is given, minimum fluidization velocity also given. Now, we calculated the bubble rise velocity, thus we can calculate the bubble velocity. So, bubble velocity U0 superficial velocity is given 0.25 meter per second, 0.25 meter per second minus minimum fluidization velocity is given 0.21 plus bubble rise velocity which is 0.3521 meter per second. So, adding this is coming, bubble velocity is coming 0.3921 meter per second. So, bubble velocity we got, bubble rise velocity we got. Now, comparing this bubble and the emulsion velocities. Here emulsion velocity UF we can calculate, and that is which will be UF, which is UMF divided by epsilon MF that is fluidization velocity with which both solid and the gas is moving, that is the emulsion velocity also. So, here bubble and emulsion the comparing this bubble velocity with the emulsion velocity. First emulsion velocity you can calculate, which is UMF by epsilon MF, that is UMF is 0.21 divided by epsilon MF is 0.45, it is given. So, emulsion velocity is coming 0.467 meter per second. Now, UB by, when we are comparing this UB by UF, what ratio it is coming? So, let me find out the eraser first. Let me rub this. Now, UB by UF, when you are comparing this UB by UF, this is coming 0.3921 divided by 0.467. So, this is coming 0.84. This is less than 1. UB by UF, that means bubble velocity here as it is coming less than 1 means bubble velocity is less. Here the fluid velocity, the emulsion velocity is more than the bubble velocity. So, when your UB by UF is less than 1 indicates that reactor is operating in the slow bubble regime, which we discussed, that is the when the particle size increases further, the bubble velocity slows down. So, here it becomes the 0.84 as less than 1. So, it is operating in the slow bubble regime. So, here delta we can calculate, because we need to calculate the Kr dimensionless reaction rate also, that is Kr tau. So, for which we need the delta. So, delta we can first find out, that is U0 minus UMF by UB plus 2 UMF. So, when you are calculating, that is substitute now U0 we know, UMF we know, UB calculated, so we can calculate this. So, it is 0.25 minus UMF, that is 0.21 divided by 0.3921 plus 2 into 0.21 UMF. So, this is coming 0.0493. So, fraction of the gas in the bubble, it is coming as the delta, it is 0.0493. So, now the reaction rate that is for the plug flow reactor, considering that. So, 1 minus x a we can calculate. So, let me rub this. So, 1 minus x a for the plug flow reactor model we are considering equation, which is exponential minus K r tau. In place of the tau we can write L f, that is volume of the bed, 1 minus L f into 1 minus epsilon f divided by u0 Kr into tau. This is the tau expression because volume of the solid, how much time it is remaining in the bed, residence time of the solid particles. So, Lf into 1 minus epsilon f, that is the volume of the solid particles, and this is the superficial velocity. So, this much time tau it is remaining in the bed. So, into your u0 by UMF into 1 minus delta. This expression already we have discussed, that is this will give you the 1 minus xa. Now, all the data we know, so we can calculate this 1 minus xa as exponential, substituting all the values, minus here Kr is given, Kr 1.5 meter cube of the gas per meter cube catalyst per second. So, minus 1.5 into Lf 0.8 is given into 1 minus epsilon f is given 0.42 divided by u0 0.25 into, just let me rub this term we have to multiply now, u0 by UMF 0.21 by 0.25 into 1 minus delta, delta already calculated 0.0493. So, thus this is coming 0.1084. So, your 1 minus xa is 0.1084, that means 1 minus xa means how much not consumed, xa is fraction getting converted. So, 1 minus xa not converted. Now, xa we can calculate from this. So, 1 minus 0.1084. So, this is coming 89.2. That means, here gases conversion is 89.2% it is coming. Now, the dimensionless reaction rate we can calculate, which is Kr into tau So, Kr is 1.5 into tau, it is 0.8, that is Lf into 1 minus epsilon f, which is 0.42 divided by u0, which is 0.25. So, thus this is coming 2.784. So, dimensionless reaction rate constant we got 2.784, where it is reaction rate constant it is given, and that is dimensional, which is 1.5 meter cube per gas, meter cube of the gas per meter cube of the catalyst per second. So, Xa we got, that is percentage of conversion is 89.2%, gas is getting converted, and the dimensionless reaction constant is 2.784. This is for the third type of the third model, which is the large size particles, that is we considered. So, you can just see just it is visible now. Yes. So, thus we got calculate the conversion we calculated 89.2, and and dimensionless constant also calculated. Now, this is here slide. So, so, reactor model for the bubbling bed of the large size particles where the bubble movement is slow. Similarly, for the other also you can do, but it is time will not permit, just 2 minutes I will just say that here. All cases we are considering the plug flow in the fluidized bed reactors. The models we consider is the plug flow reactor. Suppose we consider the calculation is there. Suppose here another example is there, but question I have not typed here. In the first type model where the for the fine particles, just the last things you can see. Bubbling bed model for vigorously bubbling bed where the bubble velocity is much higher than the UMF. So, we can just write the last here the reaction rate, it is Kf, it is given by as lengthy there. I just simply small example one considered gamma b into Kr for the fluidized bed. The final rate constant reaction rate will be here gamma b into Kr plus 1 by K B C plus 1 by, I will just explain this and with that we will finish, gamma C into Kr plus 1 by K C E plus 1 by gamma E into Kr. This is the, because here there in the model as I told, the bubble to cloud, it is the reversible cloud to bubble, bubble to cloud, then the emulsion to cloud, cloud to emulsion. So, all the again the emulsion to bubble is there. So, that is why here B C, that is bubble to cloud. So, reaction rate constant when the gas is moving from the bubble to cloud. So, reaction rate constant bubble to cloud. Now, it is the reaction rate constant in the cloud only. If you Kr, if multiplied with the fraction which is remaining in the cloud, and it is the cloud to emulsion, then it is the fraction remain for the gas remaining in the emulsion, gamma E into Kr. So, thus here it is in the bubble, fractions remaining in the bubble. So, thus it is as in the different phases reaction takes place. So, here the final reaction rate, because in the reactor it is when one will calculate the overall reaction rate, one will calculate. It is not that how much is bubble to cloud. So, that separately we will calculate. Again finally, we add all the things. So, here emulsion, then cloud to emulsion, whatever the movement is there across the boundary, then the in the cloud also some reaction taking place, and the bubble to cloud, and then the in the bubble also. So, taking the all this, the Kf is calculated, then 1 minus x a is calculated, which is exponential, as it is same I told that it is the plug flow reactor is it is considered Kf, that is overall reaction rate, into delta Lf divided by U0 U0. So, which is equal to exponential minus Kf into Lf by Ub. So, this is for the first model. Now, for the second model, just similarly you can, where the intermediate size particles are there, here in symbols we can write here where the second type of the model intermediate size particles, we can just, it is the 1 minus delta into UMF equal to 1 minus delta into 1 minus epsilon MF into Kr into CAE minus delta KBE into CAB minus CAE. So, here as I told, cloud will not be there. So, bubble and the emulsion will be there. So, it is the concentration of the gas in the bubble CAB, concentration of the gas in the emulsion, and here the fraction of the gas remaining in the bubble delta, and here thus we can knowing this, from this we can get the Kr reaction rate, and whatever the reaction rate will be there, if you multiply with the time tau, then we can get the dimensionless reaction rate. So, third type we know. So, fourth type the example we discussed. Fourth type, as it is in the freeboard region. Freeboard region, the KFF, the bubbling bed model, where it is KFF in the freeboard region, sorry, 1 minus x, last one we can write instead of writing this. One minus x a, that is after means how much gas remaining, that constant fraction, that is 1 minus x a is exponential minus K f f into delta L f divided by U0. So, here first K f f we can calculate, which is in the core region, that is in the main bed region, what is the gamma fraction remaining, reaction rate constant will be plus 1 by k dash B e plus 1 by gamma wall into K r. So, overall that is as in the main bed region some reaction is taking place and also free bed region reaction is taking place. So, it is in the when the transfer is there from the bubble to emulsion, bubble movement is also there, but not much. So, it is K dash B e. So, bubble across the bubble and the emulsion, because fluidization always takes place because of the bubble, whether the fast moving or the slow moving bubbles or the bigger size bubble or the smaller size bubbles. So, here it is the across the bubble emulsion boundaries, so it will be K dash plus it is the fraction of the gas remaining in the core region, main bed region, in the wall region means here in the free bed region. So, thus we can get the overall that is reaction rate, and substituting that we can get the 1 minus x a. So, this is about the fourth type of the, that is where the in the free bed region also reaction will be taking place. So, this is some things just in short about the different type of the catalytic reactor, where the gaseous reactant gets converted and the reactions proceeds, and thus knowing all this we can apply this knowledge for the treatment of the gaseous effluent, because if how much gases निकल गए क्या? I don't know whether by mistake I. So, knowing the conversion of the gaseous reactant, we can use first if we collect some gaseous effluent or we install the fluidized bed reactor, whether catalytic or the non catalytic. Usually for the treatment of the gaseous effluent, it is better to use the catalytic reactors, so that knowing that concentration of the gaseous pollutant in the industrial effluent, gaseous effluent, we can treat in the fluidized bed reactor, where how much gas pollutant from the gas is getting converted, and that we can calculate. Accordingly, we can estimate what is the initially we can carry out the experiment in the bench scale model, then accordingly we can design the pilot plant unit, which can be installed in the industries, such that so that the gaseous effluents can be treated properly before emitting directly to the atmosphere, which will save the environment to some extent. So, this is all about this in brief about the catalytic reactor and its role in the treatment of the that is gaseous effluent, and in turn to we can move a step to have a sustainable environment. Thank you. Any questions? Okay, if you do not have any questions, so we can stop here. Okay, thank you all. Okay.